Yeah, it's real interesting looking at the program for this school. It's kind of like the old folks home, come and talk to the young folks, you know. Jim Demmel and Jack Dongera, and now Tim Mattson, and, you know, yeah. Though IcePack was foundational to me being able to do my PhD research. So I love that package, and I remember it well. But now let's talk about OpenMP. This is changing gears, less mathematics, more computer science stuff. Does that sound okay and fun? All right, good. Yeah, you'll be able to understand what I say. Okay, I work for Intel, which means I have to put this up, which basically says, do not sue us, and you may not be able to reproduce any numbers I show you. Okay. That's what that says. I love lawyers. So there's slides you can download online. I know you can all find them. And this slide is really not one I'm going to walk through right now. You have it to refer to. But it talks about where you're going to get the exercises, where you can get online, where you can do this work. I do things differently than most people. It has been shown in numerous studies that the least effective way to teach people is to lecture. I find it kind of interesting that that's the foundation of how we teach. And I just refuse to do it. Sorry, it sucks. No, I'm determined on actually helping you learn OpenMP. So we're going to do very little, as little lecturing as I can. It's still going to be about 50%. I'm sorry, but as little as we can. But a lot of is active doing things online. So this is really important. You know, download your PDF of the file. So when the time's right, you can come back and refer to this page. But you know, you can do the exercises on Vesta. You can do them on Cooley. And here are the instructions on getting the environment up for that. You also have the option of doing it on your own laptops if you have a GCC compiler, or if you're really special and have an Intel compiler, because they're awesome. So anyway, there's a GitHub where you can get the slides and all the exercises as well. So there's multiple ways for you to get at them. But you can get back to this page in a moment here. I don't want you to pause right now and get all that set up. I want to finish my preliminaries here. So I'm a professional kayak coach. And this is where I've really learned, and they drill into our heads when you're trying to coach athletes, that people learn by doing. They learn by guided discovery. They learn by giving something to do, and then by struggling to do it, they learn it themselves. So that is my goal. I have not achieved it entirely, but that's what I'm working for this system. It's active learning that I'm stressing. So in the exercises, when you get them, there is a folder called Solutions. Do not cheat. Do not look at them, okay? You're not being graded. If you have problems with an exercise, no one's going to look down on you, all right? I've actually done this before where people go into the Solutions section, copy the solutions in, change it a little bit, and say, see, I'm smart. I did this exercise so fast, all right? So the Solutions folder is there for your own study later on. Don't look at them. But all the solutions, the exercises are there. I want you to learn and play around. Now, nobody has any excuse to ever get bored. Some of you out there are already OpenMP programmers. Some of you out there maybe could deliver this lecture instead. You know OpenMP so well. If you're one of those people, then I draft you to be my teaching assistant. You know, when others seem stuck, if you finish the exercise, help them. The room should get noisy during the exercise sessions. People should talk and exchange information. There is a lot of truth to the saying that the best way to learn is to teach. So if you're one of the OpenMP ringers out there, expect to do a lot of teaching. The other thing is play. You know, oh, we did the exercise with 4 threads. How does the system screw up if I ask for 1,000,000 threads? You know, what if I run the loops backwards? What if I change? What if I block it and see if I can get closer to peak? You know, I mean, there is endless variations you can play with. So nobody should ever have an excuse to get bored. This is a place to play and learn deeper if you already know a great deal. So I guess that's it. Let's get started. So this is basically we're going to spend the rest of today getting you deep into OpenMP. And what I'm going to focus on is what I call the Common Core of OpenMP. And this is the 19 constructs that people use all the time. That's going to be our focus. So here we go. OpenMP. OpenMP, it's an application programming interface for writing multi-threaded code. That's one statement for it. That's great. Most of what happens in OpenMP is at the level of compiler directives. And the reason we do that is our kind of philosophical dream is that you start with the serial code and you add directives that are largely semantically neutral to tell the compiler what it should do to make it a parallel code. And when you're all done, you have a program that is semantically the same, whether it runs on multiple threads or runs on a single thread. Now, yes, you can get clever and break that. There's lots of cleverness you can do. But that's kind of the overarching use case we had in mind. And directives are a great way to do that, because a directive, if the compiler doesn't understand it, it skips it. And it gives us a very low-touch way for you to go in and tell the system how to make it a multi-threaded code. It's all about making it simple for you to write multi-threaded applications in Fortran, C, and C++. It's all about simplicity. So it's not about generality. No one would ever claim, well, they might claim, but if they ever do, tell them to their face they're stupid, that OpenMP is a general multi-threaded environment that can do everything. You know, I would never write a low-level concurrent print server to work very closely with my operating system in OpenMP. I'm sorry, I wouldn't do it. It's not for that. It's for real scientists, physicists, chemists, people who want to solve a problem and they don't want to spend the rest of their life in low-level pthread code. So it's all about easily getting you multi-threaded code. And OpenMP is probably my proudest achievement, because I was there from day one. It is really awesome, and it is really boring, because we know what it means to standardize, right? Standardize means you look at an existing practice and you say, can we please all agree how to spell parallel do? All right, that's basically what we did. So, you know, it's boring by design, because we looked out there what the best and smartest and most clever people were doing in symmetric multiprocessing programming, and we said, let's standardize it. Let's all make what we know how to do consistent. So that's the high-level overview. Now, OpenMP has grown an awful lot from the dark, dark days when I started way, way back in 1996 when I started working on it. And when it started, this is the pages of the spec, and I removed the appendices, and so this is just like the core of the spec. So when it started, it was like 45 pages. It was real simple, Fortran only, then we added C, then we updated Fortran, so we went along. And what you can see is as time goes on, you know, by 3.0, when we added tasking, it grew to 150 pages. 4.5, the latest spec, is just over 300 pages. The spec coming out this November, I don't even know. I would be surprised if it's under 400 pages. So, you know, because of all the stuff we're adding. So the complexity of OpenMP has just exploded. And it's, you know, it's easy to criticize that. But, you know, this is what happens as a standard is successful. The same things happen to MPI. I can make a slide probably very similar to this for MPI. You know, if you're successful, then more hardware comes along you need to support. We now support GPUs. You know, if you're successful, more people will try to use it, and they'll find new algorithms you didn't think about. So you have to support that. So this is what happens to any successful standard. So, you know, I'm not making fun of OpenMP, but I am recognizing the frustration, because if I just handed you 300 pages of spec and said, here's a simple way to program to create a multi-threaded program, that's easy, just do it. Yeah, you'd look at me like I'm a nut, which you may think I am anyway. So at any rate, this is why I learned, and in fact, the MPI people have been doing this for years. I've just started doing this the last couple years with OpenMP. Is instead of trying to give a tutorial where I cover the breadth of OpenMP and guarantee that you will all walk out of the room with your head spinning, Instead, it's like, no, let's just focus on the 19 constructs that every OpenMP programmer uses all the time. And frankly, most OpenMP programmers never use more than those 19 constructs. So the idea is you master those 19 basic constructs, what we call the Common Core, totally master them, and then go to the spec when you hit something additional you need to do. And if you do that, then you can absorb OpenMP and have a long, happy life with OpenMP, and everything will be wonderful. And that's what we want. Okay, so let's get some basic definitions out of the way. The core of OpenMP, and this is where I want to start, is OpenMP really was designed around a symmetric multiprocessor system. We've added stuff for NUMA, we've added stuff for GPUs, but let's just start with where OpenMP began. And in a symmetric multiprocessor system, that picture captures it. You have a collection of processors, and they see a shared address space. And they all have equal time access to that address space. We know that's bogus, but you know what? That's the model. That's the SMP model. Now, on top of that, you have the system layer. And there's the operating system, which understands these multiple processors and understands some concept of a thread and some concept of how to manage a shared address space. OpenMP inherits and uses that. So most implementations we call p-threads, but it's whatever the operating system gives us for a threading layer, that's what we're going to use. And then the people behind OpenMP implementations create this OpenMP runtime library. And you just use it. You don't touch that, it's just there. But it calls the systems, the services from the operating system to run on top of the multiprocessor hardware. All right? I sometimes get people ask me, I have this p-threads program, would it run faster with OpenMP? And I say, well, probably not unless OpenMP lets you do different algorithms, because OpenMP probably calls p-threads. Now we come to the part you need to learn, the programming layer. So the set of directives, which is what we will step by step learn. There's a small number of runtime libraries. So a directive tells the compiler, do this for me. Directives are all about compile time transformations. The runtime library is the OpenMP library. This is about things you can only find out on a running program. How many threads do I have right now? You can only do that when the program's running. So that's a library routine. And then there's a small number of environment variables which come at execution time. Let me tell the system what the default number of threads should be, for example. And then, of course, on top of that are the applications, and then the end users running the applications can interact with the environment variables. So this is a cartoon that gives you an idea of the components and the layers that OpenMP fits in on. So the basic syntax. Now, this course, this tutorial will be taught in C. Because I'm an old guy, but I still believe that anybody who does high-performance computing needs a reading familiarity with C. You should know enough C so you're not scared of it. Now, what I'm going to tell you here is you don't need to use any of the weird, obscure corners of C. We're not going to do multiple layers of indirection. In fact, I think you can do this entire tutorial without doing any layer of indirection. I'm not sure you ever need to use a pointer. So, it's very, very basic C. Now, in the exercises, because I know there's some of you who are Fortran programmers mostly, which, by the way, just as an aside, all right, for you Fortran programmers, when God was doing the simulations to drive the creation, she did all of those in Fortran 77. So I'm very serious. Fortran 77 is God's language. So I'm very fond of Fortran. but it shouldn't be. But for those of you who are coming at this from Fortran, or I don't know if we have anyone who only knows Python. If that's the case, I feel sorry for you. But there's a file in the exercises called Learning C. And it's an executable file. And it basically, if you read the comments and play around with it, you can run it and play around with it. It covers like 90% of every C concept we are going to touch in this tutorial. So you will be able, during a break, spend 10 minutes playing with Learning C, and you'll be got right up to speed with C. But just in all seriousness, you cannot have a career in high-performance computing if you do not have a reading familiarity with C. even if everything else you're going to write is in Fortran. And we can talk about that more and more later. So at any rate, the syntax of a directive. In C, directives to the compiler occur through things called pragmas. So it's going to be that pound, pragma, OMP, the name of the construct, and then an optional sequence of clauses. And that's what's going to look like. So for example, pound, pragma, OMP, parallel, private, X. All of that will be explained later. That's an example of a pragma. And that's a directive to the compiler that says something. Now, at the top of your program in C, you're going to have to tell the system what are some definitions of function prototypes, special types, constants. Those are all put in an include file. So at the top of every OpenMP program will be pound include angle bracket omp.h close angle bracket. All right? Does that all make sense? Now, the next concept, very simple concept, is what I mean when I say a structured block. So a structured block, very simple. It's a block of code. It will occur, it's either one line or multiple lines between curly braces. C is a block structured language built right into the language are these block constructs. They're the curly brace open, curly brace close. In between those is a block. And a structured block, very simple. It's you make a promise to the compiler that you will only enter at the top of the block and you will only enter at the bottom of the block. You can put an exit statement in the middle, but that says shut down the whole program. So that's the only thing you can exit out of the middle. So you're not going to jump into the block. You're not going to jump out of the block. You enter at the top. You exit at the bottom. Simple concept. Very simple. Remember, OpenMP is about simplicity. So, and we're simple. It's because we're wonderful that way. All right, so we now come to the first exercise. And I want you to write a hello world program. All right? And what this is really about, though, is you finding what system you're going to work on. Make sure you can get on that system. Make sure you can find an editor, and that you can type in these commands, and that you can find the compiler you're going to use, and you can execute it to run this program. Thank you. So how many people are done? Many of you. OK. I guess since you've done the MPI exercises and already, you already know what system you're on. So this was really, really quick. All right. Let's move to the second exercise. And so this first exercise was, do you know how to use a text editor and a compiler? You would be surprised how often this is a 20-minute ordeal. So here's the next exercise. Do you know how to tell your compiler to use OpenMP? So we're going to explain everything. What I just want you to do is put pound include omp.h at the top, and just put pragma omp parallel open bracket, then your unchanged hello world, and then close that bracket. And then, unfortunately, my compiler statements there probably don't match with the ones you need, but that's from that previous first page. But use the compiler you did before, but you need to tell it, link and do everything for OpenMP, and then run this. Now, I'm just curious, are any of you working on Cooley? OK, did you get ICC to work? You did? OK. Because last night it wasn't working for me, because probably it recognized I was from Intel and spit all over me. So GCC works there as well. OK. It's just a little bit irritating because on ICC it's -Q OpenMP, on GCC it's -F OpenMP. Oh well. All right, so there was the OpenMP include file. I'm going to describe it in excruciating detail later, but this pragma creates what's called a parallel region, and it's a block structured language. So here's my structured block, and this is the close of that block. Okay, and when I run it, I get something like this, and it might be different every time I run it. You know, hello, hello, world, world, hello, hello, world, world. All right, that's kind of weird. Wait a minute, I thought I said hello world. Why is it mixed up like that? So this is an important concept. I'm going to say it probably 6 times, and maybe I should say it 16 times. All right? In multi-threaded execution, the operating system on your behalf is scheduling the threads. You do not explicitly control that. You do not have any control over which thread gets into the right buffer at which time. What we say is that the execution of the statements in your program will be interleaved. So their execution is interleaved. And your challenge as a programmer, this is what makes multi-threaded programming so much fun. I stay positive. So much fun. It's why we enjoy it so much. Is you have to analyze your code so that every conceivable way the system could interleave the instructions is correct. I call it the multi-threaded reading of your code. In this case, it's not a big deal, but you just have to expect that, oh yes, it'll interleave it every which way. It could serialize them, it could interleave them, it could leave them every which way. All right? Now, the I/O libraries on every known system I touch today are thread safe, which means it's perfectly OK to have multiple threads hitting a printf at the same time. And notice we're not breaking up individual write records. I'm not getting hell, war, dull, we're not breaking up individual write records. That's because the I/O library is thread safe. They went through and they carefully put the right hooks in so that multiple threads could hit the library at the same time and it would do the right thing. So the I/O library is thread safe. That's why they correctly interleaved. But this concept of every way they could be interleaved, you have to make sure all of those ways are correct. And believe me, that will be very important as we move forward. All right, I now want to talk about creating threads so that you're thinking many threads before lunch. The core model behind OpenMP is the fork join model. You've seen this phrase many times. Let me describe it ad nauseum with the right context for OpenMP. So your program starts up and you have an initial thread. That's that red thing. And it's cruising along through the code, and it hits a point where, gee, it'd be nice to have some threads helping me. So it's going to create a team of threads. We call this parallel regions. Okay, so it's going to create a team of threads. Notice that it is the first member of that team of threads. It is the master of that team of threads. And so that's why I have it red there. Let's just look at the first one. So it's going to create a team of threads. And in this case, I have 4 of them. They're going to execute together. So it's going to fork off the team. The team executes. And when the team is done, they join. So a fork, you create the team of threads, join. They all join back together and logically go away. And after the join, just that one initial thread continues until it hits another point in the program where, hey, I really could use some help here. So it creates another team of threads. Notice it doesn't have to be the same size. I can have different numbers of threads in each team if that's what I want or if that's what the system thinks I want. So off we go. And so it continues that your program is a sequence of parallel regions interspersed by sequential parts. So this is the official OpenMP jargon, parallel regions and sequential parts. And you can nest them. So I could, in one of the parallel regions, cruise along and go, no, I really, really do need more threads. Fork off more threads. Okay, most implementations of OpenMP don't like it when you do that, which is a shame. I love that concept, but it's there. It's supported. You can do it. All right? So let me go through in detail how this looks in a piece of code. So here I have a very simple code, and I'm going to create a 4-thread. I'm going to request a 4-thread team of threads. So here I go. I have an array of 1,000 doubles, and I'm going to request by the OpenMP runtime library OMP set num threads 4. So that's me saying to the runtime system, I really would like the default number of threads anytime I ask for it to be 4. So there we go. Then I have my pragma OMP parallel. That's going to create a parallel region. And the structured block will be executed by each member of the team. Okay, so this structured block will be executed by each member of the team. Now, just like an MPI, you're all MPI experts right now. And what are the first things you do in an MPI program? Who am I and how many of us are there, right? Okay, well, the who am I is int ID, so I'm going to create an integer. I'll call it whatever I want. Here I call it ID, but I call this second OpenMP runtime library routine I'm going to tell you about, OMP get thread num. So that'll give me a rank, just like the rank in MPI, 0 to the number of threads minus 1. So now I know the ID. Now, since I declared it inside the structured block, it is local to each thread. So every thread sees a shared copy of A. Every thread has its own copy of ID. So off they go. They're going to do their computing. And actually, I have pieces of this. So there's a runtime function to request a number of threads, a runtime function to get the thread ID. Now let's look through the execution of this, because this is something you deeply, deeply have to understand, or we can't go forward or do anything at all. So here I have a little box. I have the code. Let's look at how it executes, and let's look at how the data is shared in this execution. So I start the program, and I'm going to put, now if you think about it, I have a process running in my operating system. That process will have threads that are part of that process. In the process is a region of memory managed usually as a heap that is visible to all the threads. So I'm going to create this array, and it's going to sit in that memory of the process, owned by the process, in a heap, visible to all the threads. I ask for a default number of threads. Now I create the team. Now, inside that code, I call a function, and I declare my int ID. So as you can see, I'll have a thread poo0, poo ID1, poo ID2, poo ID3. All right? Does everyone see it? Is it clear how if I declare it inside the structured block, it's local to a thread? If it's declared outside the structured block to a first order of approximation, we'll expand and complete these rules. But kind of the easy thing is if I declare it out here, all the threads see it. If I declare it in here, only the threads see it. Pretty simple, right? Right? It's pretty awesome. Yeah. So let me mention that we have this runtime function, OMP set num threads, and that requests a number of threads. You don't know if that's the number of threads you get. Now, this may seem really weird. I ask for 4 threads. Just give me 4 threads. And on your own laptop, it mostly will. But what if I asked for 10,000 threads? Some of your laptops may go, I don't want to run 10,000 threads, or they might. Or what if it's a shared system? Okay, so there's a 1,000 core, 1,000 processor system, each one with 24 cores, because it's a really nice Skylake. And we all like Skylakes, don't we? Yeah. So you got lots and lots and lots of cores. And the system may constrain how many of those cores you're allowed to grab. So the system may have limits on how many threads you actually get. So that is specifically designed in OpenMP to be flexible. You don't know how many threads you'll actually get. So int n threads, I've declared an integer. I'm calling it n threads, OMP get num threads. So now that tells me how many threads are in the team. Now, it may be different than the number you asked for. So if you write an algorithm that absolutely says, I must have 4 threads, if there's not 4 threads, this algorithm will break. My first comment to you is, you are a bad programmer. You shouldn't write algorithms that way. But if you really do need 4 threads, then you need to check OMP get num threads. If it's not 4, exit, because you can't continue, because you didn't get the number of threads you wanted. It's a subtle point, but it's one I want to make sure you understand. You request a number of threads, but you have to check that you actually got that number. All right. So there's that. The word comes up from time to time, so I want to define it and get it over with. So the OpenMP runtime controls the environment, and we have to define all of that in the spec. And we need to be able to control the scope of how all these things work across different features of OpenMP. We do this through the concept of something called an internal control variable. And it's an opaque object. You will never see it, but it just acts like it exists. And it basically defines defaults. So when I'm calling OMP set num threads, what I'm actually doing is I'm setting an internal control variable for the default number of threads. And later on, we'll talk about an environment variable, OMP num threads, which does that at program startup. But what they're both doing is setting an internal control variable. And you'll see a pattern. It's going to be OMP set num threads, so OMP set the internal control variable. And then notice there's the flip side, OMP get the value of the internal control variable. So most of the internal control variables have that pair. And many of them have an OMP set, an OMP get, and an environment variable. So this is just a concept I want in your head. But I have talked at you so long, and I apologize for that. All right, here is the program we're going to spend a lot of time playing with today. This is often called the Hello World program of parallel computing because it's probably the simplest program we can think of, where the code fits on one slide, and it's easy to work with, and it actually will show speed up if you do everything right. So this is like a wonderful place to start up. Now, it's great that you are all hanging out in an HPC context. You have enough math. I probably don't need to explain what this stretched S means, right? OK. These days, I actually encounter people who don't know what that means. And it's like, whoa, this is weird. OK. So I have an integrand selected that if I integrate it from 0 to 1, I know it equals pi. So this is nice. We know if we get the right answer. I'm going to replace it by a sum to get the area under the curve. We're going to compute all these little rectangles and sum them together. And we should get something that looks like pi. And that's the program. You have the program. It's called pi.c. And there's one other little thing I want to mention. You can check your time with an OMP get W time. Notice that's pretty much the same as the MPI. That's deliberate, because MPI is even a little bit older than OpenMP. So, double a variable, get me the time right now, then I'm done. I do the difference between get time and that variable. It gives me the elapsed time. All right, so now we come to your first exercise. But I want you using only, OK, OpenMP ringers. I mean only the constructs on this slide. Don't use any of the others. You're going to use an OMP parallel. You can use the get num threads, get thread num, the timer, and set num threads. Only using those, parallelize the program in pi.c. Now, save pi.c, because later on we're going to go back to it. So make a copy of pi.c, and then parallelize it just using these constructs. What we're going to do right now is start the exercise. So start from that pi.c. And those of you who've already finished it, optimize it, play around with it, explore. But start from that pi.c and think about what you have to do to create a structured block that you can execute on multiple threads that will correctly do that loop in parallel. We're going to spend a good 10, 15 minutes on this. That should be enough time, given that you've all been through MPI and parallel computing is not new to you. That's one thing. This group goes faster than most people I work with because you've been through the MPI course. Parallel computing is not brand new to your brain. So things tend to go a lot faster. So let's spend about 10, 15 minutes and see if you can do that one. Remember, the big challenge is you're going to have to do a whole block of those loop iterations per thread. So you have to figure out how are you going to split up the loop between threads. Then the other challenge, and this is the one that can get a little tricky, is sum. OK? Sum. That is fundamentally a shared variable. You want to accumulate that per thread. And then you want to combine all those values from per thread. Now, the C language is a block-structured language. Variables declared inside the block disappear when you go outside the block. All right? So I can get around giving each thread its own private copy of a variable by declaring it inside the block. Great. Now each thread has its own copy. But at the end of the block, at the end of that closing curly bracket, all those variables go away. So the partial sum that each thread accumulates has got to be in some kind of object that's going to survive beyond the close of that block. It's got to sit in a global space. So think, how would you do that? And if you don't have an answer, turn to one of the people around you and say, how did you do that? And then if the two of you don't know, spin around in your chairs and look at the people behind you and ask, how did you do that? Okay? So you need to figure out, how do I create a way to hold the partial sums so that later on, when I exit the parallel region, I can combine them into a global sum? That's the tricky part. Now let me emphasize, with a group this size and the skill sets all over the map, we have cheaters in here who were using OpenMP constructs way beyond what was here. You know who you are. You should hang your heads in shame. But so we have people who are experienced OpenMP programmers. We have people here who know more C than I do. We have people here who are not C programmers. We have people here who have never written a parallel code until they showed up here a day or two ago. So with that skill set across the room, we're not going to keep everyone evenly right on step. And that's just the way it goes. Now, we have how long for lunch? A whole hour or 90 minutes or 1 hour? OK. The way this works is we get a little bit out of phase, and that by the time we get to lunch, some of you should just dash off to lunch and some others should stay behind, and we should talk and try and catch you up. Some of you during one exercise will complete the previous exercise. There is no physical way to do this with everyone all lockstep right together. And it's OK. The process works. So I'm going to go on and show my solution to this exercise. And it's not the only solution, but here's what I did. So I'm lazy, and I want to use as little of the C language and environment as possible. So I define a constant for my number of threads. It's not that hard for me, but the people around you, it's really hard if there's other talking. OK, so I set the number of threads as a pound define. So now I'm going to have my pragma OMP parallel. Of course, I have to have that. I need to know which thread am I. I need to know how many threads there are. I'll explain this line in a second. And then I do the simple thing that MPI programmers do all the time. It's a cyclic distribution of the loop iterations. I just go for ID, for I equal ID, less than the number of steps, increment by the number of threads. So it's a round robin distribution. It's like if I had a deck of cards and I was just dealing them out to the threads. Thread number 0 will do, if I have, thread number 0, if I have 4 threads, we'll do iteration 0, 4, 8. Thread number 1, we'll do iteration 1, 5. So this is the lazy way to split up that loop. Okay? Another way to split it up, though, that a lot of you did, is you compute a block. It's like, oh, if I take the number of steps divided by the number of threads, and you're going to do ID times that block size to ID plus 1 times the block size. You just compute that. All right? Perfectly fine. But you have to somehow figure out how you're going to split up that loop. Now, here I have x, and notice I declared x inside the block. If I didn't do this, this is a really common mistake. If I didn't declare double right here, if I instead picked up the double x from up there, which isn't there, silly me, then it would be shared. And if it's shared, I now have every thread reading and writing into it. At any given moment, I don't know what thread's going to load when it goes to load x. That is called a data race. Can everyone see that? Data races are the enemy in multi-threaded programming. This isn't an OpenMP thing. This is every time you touch a multi-threaded environment, TBB, OpenMP, P-threads, C-threads, I don't care. The bane of your existence as a multi-threaded programmer is this case right here. because the compiler has absolutely no way to know that that is a mistake. The compiler can't warn you. There are tools that can help you, but ultimately, especially given pointers and indirection and all the different things you can do in a programming language, there is no way for any tool to provably show that you do not have a data race. So you have to be very, very careful. So that's one of the common mistakes, is that people forget to declare double X right there. All right, so now what I did is notice that sum, which in the serial program is just a simple scalar, I've promoted it to an array. We call it promoting the scalar to an array. So I declared an array with the number of threads as the length, and now I can sum with index ID, and each and every thread has its own safe copy to accumulate the partial sum. Then when I get outside the parallel region, all the variables declared inside here go out of scope. I goes away, ID goes away, n threads goes away, x goes away. Okay? When you go outside the block in a block-structured language, the variables declared in the block go out of scope. But because that array was global, I declared it before, it's still there, and I can do the sum to get the final pi. And this works. Now there's one last little thing I want to point out, and then we'll go to questions. That's this line right here. Okay? Now, n threads, NTHRDS, I made private to every thread. They all got their own copy of it. But then for one of the threads, I copied it into the global scope. All right, do you see that? Now, this is a very subtle point. For many, many years, I was lazy. And I wouldn't do the if ID equals 0. I would just say the global n threads equals the local n threads. You know what? Everyone's writing the same value, so what's the big deal? And eventually I came to realize it is a big deal. So let me tell you. On an Intel chip, you don't need this, which is why I learned to be lazy. And the reason is the memory model of x86 is very forgiving. It's because Intel is a benevolent and dear and wonderful company. We created a memory model that protects you from certain mistakes. Basically, if you're doing a load, if you're doing a store of a single value, it does it atomically. So you can't interrupt a store. But if you move like to the ARM, or I believe the Power architecture, it doesn't do that. It doesn't protect you. And therefore, you can get all sorts of garbage because everyone, even though it's the same number they're storing, those stores can conflict, and you can end up with garbage. And it's a data race. All right? Subtle point. But remember, my goal here is for you to learn these subtleties about threads that you can carry with you. And you must always write code. Even though part of me, because I hope to retire someday, and therefore I want my Intel stock to be worth a lot, and I want all of you to commit that you will forever use Intel parts until the day you die, of course that would be stupid. You have to write code thinking it could go to any architecture. And that means, don't take advantage of the niceness of the Intel memory model and write it for whatever memory model you're going to end up with. Any questions about this code? I think you raised your hand first. Yes?
Can you explain why you do the pound define instead of using just an ordinary int?
Why did I do the what?
Pound define num threads instead of int num threads equals 2 or something like that.
Pound define num threads? No reason. I could have defined it. I could have defined it as an int. This makes it a constant. It's done at compile times, pound define num threads 2. So at compile time, it substitutes that number, that literal in there. So it doesn't happen at runtime. But I think if I did it as a file scope, a good compiler would have done the same thing. So no particular reason. To my style of C programming, if it's a constant and it's something that could be known at compile time, it just seems cleaner to do it as a pound define. Was there a comment on there? Yes?
So I think it's for the sum, also the array, given that you're declaring it.
Yeah, since it's the array, it has to be something the compiler knows the value of the literal at compile time. Yeah, it can't be a variable there. If I want to do a variable, I'd have to do a malloc, but then I'd have to get deeper into C, and I'm trying to stick to the subset of C everyone can know. OK, there's another question and another. Yes?
I'm looking at it, I think I maybe figured it out. But since you said that you might not always get the number of threads that you ask for,
Yes.
It looks like the way that you've set up your for statement is you will always only be doing the iteration, the number of steps, because you've said it I is less than the number of steps. But is it possible that the solution that I was working on was the chunk-wise solution? So then, if my division didn't work out properly, then I might end up doing more or less steps than.
Right.
Well, probably less steps.
Probably less steps.
Okay. So the question is, am I thinking about this properly?
So I believe, though even as you're asking it, it's like, well, I need to prove it to myself. I believe this is always correct, and I will always get the correct number of steps. Now, what she was alluding to was the solution many of you used, which, by the way, has different performance features and in some case better performance features, all right, is you compute blocks and you give a block to each thread. Now, if I was doing, think about what we just heard from Jack Dongara. You know, if I were doing linear algebra in here, so I was doing repeated operations out of a cache line, you would have to block it. Okay, the only reason I did this is, well, I'm lazy, and plus, do you know how hard it is to get all your code to fit on one PowerPoint slide at a large enough font so people can read it at the back of a room? So, you know, I have to be really careful on conserving lines. But, you know, the only reason I knew I could get away with this is that, notice, I'm not doing it. There is no cache reuse issues here. But, you know, the blocks give you much better cache reuse. A common problem is what if the number of threads does not evenly divide the number of steps? Then the easy ways you compute block, you know, number of iterations divided by number of threads, that gives me a block size. OK, if there's a remainder in that division, then when you give a block to each thread, you're not going to get the right answer. You're not going to get all the threads. OK, there is a simple trick. Those of us who play these games use so much we don't even think to talk about it. But it's very simple. And I should have a slide that says this. I would have a line if ID equals n threads minus 1. I'm the last thread. My final block index ends at the last loop count. So that gives me a trivial way to write one line of code that takes care of that problem. That just says, all my blocks will be the right size, except the last block might be a little bigger because it's going to have the remainder. So it's a trivial way to deal with that problem. Yes?
So it looks like you define int I twice, once inside the...
Great question. Yes, yes, yes.
Is that so there'll be two copies of I, one that's local?
OK. I'm going to take time to answer his question slowly and carefully, because some of you here are not C programmers. And this is a little C-ism. All right? Notice that I declare I at the top of the program, int I, right after main. Do you see that? So there is an I of global scope. All the threads can see the copy of I. Now we come into the block, and I declare I again. OK? The terminology we use is the copy of I declared inside the block masks the global copy of I. So inside the block, the C language definition clearly states that it will only see this I, and that this version of I masks the global copy. That's the actual term they use in the spec. So there are two copies of I, but as far as code inside this block is concerned, there's only one copy of I. There is no way within the C language. You have to step outside the language and do weird assembly code stuff. But there's no way in the C language for code inside here to see that global copy of I, because it's masked by this declaration. Now, the other thing to remember, just to finish this is a C-ism for those of you, but I've said it many times, I want to repeat again. When I get to the end of this block, the copies declared inside the block go away. If I have a function and I declare the variables inside a function, same thing. If I have a file scope global visible variable, I declare a variable the same name inside of a function, I have masked it. But when I get to the end of the function, it goes away. So this is the scope of the variables and thinking about the scope of the variables. It's a C thing. Yes?
So then if you were to do sum threads or the sum matrix inside that open or that loop again, or that struct again, and then you summed into that and you exit out of it, would it still be 0 then? So if you accidentally made that array twice, and then
Yeah, no, I know what you mean. It probably would. Okay, so folks, this is a little weird, and we're getting a little deep into the woods here. But it's an important point. We're going to touch on actually a variation of that issue later. Okay? So the question is, if I have a value, let's say I had int I equals 0 at the top there. So I declared I, and I initialized it to 0. So now I go into my loop, I declare an I, and gosh, I've done all sorts of stuff to I in here. All right? When I get to the end, what is the value of I? It's probably going to still be the 0. It's probably the case that the compiler, when I declare this I, will give me physically different storage. But that is not guaranteed. Okay? I think every compiler I know, it'll still be 0. But I do not think the C language guarantees it. But I'm not sure. We'll come back to that. I have to move on, though, because, oh my God, we got a lot to cover. OK. I am really big on design patterns of parallel programming, because that's my book. You all should run out and buy it. It's a little bit out of date. It was published 2004, but it's been very, very successful. Yeah, I'm really, thank you, everyone. No, what I find, and in my teaching parallel computing, because I've been teaching parallel computing off and on for decades, long time. I'm really old. And what I find is if people focus on learning the fundamental patterns, that gives them knowledge that they can carry with them to every programming language. So as you move from OpenMP to MPI to TBB to I don't care, if you don't think in terms of, oh, here's a bunch of constructs, if instead you think, well, here's the pattern for implementing that algorithm, now that's transportable knowledge across programming notations. So the program we just talked about for solving pi, the classic name for this is single program multiple data. And MPI programmers, you know, the message passing world created this pattern. They're the ones that used it all the time. And since most of the old timers like me, we started in message passing, this is what we started doing in kindergarten when we first got started. Because we all started very, very young. Back in the old days, they started as parallel programming in grade school. No, so the idea is you're going to create multiple units of execution, whether it's a thread or a process, I don't care. You're going to create multiple units of execution. They're going to have a rank from 0 to the number -1. They're going to use that rank and the number of them to figure out how to split up the work, and then off they go. It's very, very simple. This is by far the most common design pattern in all of parallel computing. And so much to the point that just you spend not very long with parallel computing, you just internalize this. So when you hear anyone say SPMD, this is specifically what they mean. That everyone's going to run the same program, and they're just going to do something different depending on who they are and how many of them there are. Very simple. OK, so I ran this with optimization turned off on my laptop, and these are the numbers I got. 1.86. Oh, and I used just a buttload of steps. You know, that's the official name of that number, buttload. Big number of steps. OK, so but I got it up to 1.86 seconds on my single thread. And when I added a second thread, it went down to 1.03, then 3 threads, 1.08, 4 threads, 0.97. Yeah, this was really worth trying to parallelize, wasn't it? Yeah, great, guys. What do you think's going on? Ugh. What's going on is a phenomenally important concept. How many of you found scalability that you thought was unsatisfactory? Okay, not all of you. Wow, okay. Let me tell you what's happening. That sum array. That sum, oh, one of them, you didn't see this effect. This is why your scalability was good, because you didn't put your array inside the loop. Okay, so what I'm talking about, you avoided. She did a great job. All right? But I put this array inside my loop, right? Inside my loop that I'm going to go through millions and millions and millions of times, I'm looking up an element of an array. Okay? What's happening here is, imagine I have 4 threads, so I have elements sum 0 through sum 3. And this is a legal program. You know what? Each thread has its own safe little place to do the partial sum. There is no shared data occurring. It's a correct threaded program. However, the way the compiler is likely to lay this out, the way the system's likely to lay this out, is they design caches so that you get reuse. So they assume that if you have sum 0, the next thing you're going to ask for is sum 1 and sum 2 and sum 3, so they put them on the same cache line. So now walk through the cache coherency protocol and think what was happening when you were executing my program. Hardware thread 0 says, hey, I'm going to read sum 0. And about that same time, hardware thread 2 says, yeah, well, I need sum 2. And it's going to go to look at that cache line, and the cache coherency, the cache policy will say, that cache line's dirty. Someone else just wrote into it. All right, invalidate my cache line, flush the cache line. OK, this one is told, someone else needs this cache line. It's going to flush the cache line, sloshes through the memory, goes back over there. Great, now thread 2 can do what's right. Meanwhile, hardware thread 0 is ready to look at that sum again. What's it going to do? It's going to go to the right. It's like, oh, that cache line is dirty. Someone else has written into it. OK, invalidate the cache line, flush the cache line, send a signal. Oops, we got to flush this cache line, flush the cache line, slosh back. So what I am doing is, as I add threads, I'm just increasing cache coherency protocol overhead as I slosh all these cache lines around. So it's called false sharing, because there is no sharing. There's no actual variables being shared, but there are cache lines being shared. And because of this cache effect, I am losing my scalability. Okay, does that make sense? This is kind of an important performance gotcha that you stumble into with parallel computing. This isn't an OpenMP issue. It's any time you're using a system where you have cache lines shared between threads. So TBB, C threads, P threads, MPI. You run into this all the time. False sharing is what it's called. Now let me show you how I fixed it. All right. This is a fix. This is how a twisted person would fix it. See that sum array up there? What I just said is, oh, I'm just going to pad it. I'll just put, I'll just pick a number. Let's say 64 bytes. I think that's big enough to overflow a level 1 cache line. So I'll just put 64 there. And now you see I always index 0. But now I'm making sure that every time I go to int ID, I'm on a different cache line. All right? And sure enough, when I do that, I run on my system 1.86, 1.01, 0.69, 0.53. Hey, isn't that awesome? Isn't that awesome? Okay? Tell me, is that good coding practice? All right. I would hope the teams you work within, if they ever saw you do something like that, would profoundly abuse you. All right? Because anyone else looking at that code is going to go, what the heck does that second dimension mean? Remember, you spend more times maintaining code than writing it. So, and then what if I move on to a system in the future? Remember, the lifespan of an application is measured in decades. I'm an old guy. I turned 60 this year. I'm that old. Okay? I have a friend who's a little bit older than me, and he was telling me, this was like last year, how he was working on a piece of code with its solver, and he found a piece of code that was written before he was born. So this was a solver written in the 1950s that they were still using. So code lasts a long time. So what happens if we go to L1 cache lines that are 32 bytes? And then you try and figure out the performance glitch. This is ugly. Okay? So yeah, we fixed the problem. But man, there's got to be a better way. Like goodness, there is. It's called synchronization. Let's learn about synchronization. Let's learn how to deal with all this stuff much cleaner. All right. So I could talk to you for 2 days about this topic. This opens up this deep, dark, mystical world of memory models, concurrency theory, and it gets intense. And because the OpenMP creators are gentle and kind people, we're going to give you some simple, high-level ways that can avoid all the ugly intensity. All right? But remember, when I said that all those instructions on the threads are interleaved, that goes all the way down into that dark rabbit hole. All the loads and stores can be interleaved, all the different instruction units, and you have out-of-order cores, so they're even doing a level of out of order. I mean, the whole sense of time and what happens at any given time becomes really, really messy. So the way you deal with it is by sticking to high-level constraints on order. And as long as you stick to these high-level constraints, you're okay. And believe it or not, for most of you writing code in scientific computing, you're not going to have to go deeper. But sometime, if you have a friend who works on operating systems or works on messaging layers that have to tightly integrate with operating systems, just go up and give them a hug. They need it sometimes because they have to go into that dark rabbit hole. And they're broken human beings, and they deserve our respect. So we're going to talk about just the 2 simplest synchronization constructs that you use all the time in OpenMP. If we have time, I'll go into some of the others, and there's an appendix in these slides that goes into some of the others. But my advice for most of you is do not even look at those others, because they will scare you away and you will become an English major. Okay. So the simplest concept in synchronization is mutual exclusion. And the concept is simple. I want to have a way of saying, here's an arbitrary collection of statements, and I want to make sure that only one thread at a time can execute them. So if one thread is executing them, they exclude all the others. This is called a critical section. All right, so look at this code here. It's a common SPMD pattern. I have a variable res, which is declared outside the parallel region, so it's visible to all the threads. Then I have my pound pragma OMP parallel. And I'm going to do the simple SPMD thing. I know who my ID is. I know how many threads. And then I split up the loop. And this is key. I do a computation to get the variable b. And it's going to be a big job. This better be a big job. And it better be a big variable job, or this piece of code sucks. But imagine this is a big job. It sometimes runs 5 seconds, sometimes runs 3 seconds. It's all over the map. And it's all seconds. It's a lot. OK? Now, pragma OMP critical. What that says is that statement, that function call, res plus equals consume b. OK? That statement can only be executed by one thread. So if a thread hits the critical section and looks around and no one's executing it, it goes right on in and does the execution. If while it's executing that consume function, another thread hits the critical section, it will sit and wait. And it will wait until that other thread is done, and then it will move on. And let me just be really, really clear. I'll talk about this a little bit more. But we do all the memory model magic needed to make this work. So when I say thread is done, I mean thread is done and has committed any of its updates to memory so everyone else can see them. All right? So we do all the magic you need about the memory model so you don't even have to think about it. All you have to think about is only one thread at a time is going to call that function consume. And then when it's done, it's going to take the result, and it's going to add it to res. And I know safely one thread at a time can do that. All right? Any questions about the critical section? Very simple to use. Oh, there is a question. Yes?
So I didn't do anything fancy with these cache line things, but I still got pretty much ideal scaling up to eight threads. Is that because of the optimization flags built into the makefile?
Yes. OK, so he's going way back. This is interesting. Going back to the false sharing, It used to be I was guaranteed that everyone, no matter what optimization level, would hit the false sharing. But compilers are constantly getting more and more clever. And now at the 03 optimization level, both the GCC and the ICC compilers will detect the false sharing and save you from it. Yeah. OK. Now, there's another synchronization construct, and this is called the barrier. And as I said, most of the time in OpenMP, these are it. This is all you need. So a barrier, well, you've had this in MPI. Didn't they talk to you about a barrier when they were covering MPI? Yes? OK, good. So you know barrier. It defines a point in the program where all the threads must arrive before any threads continue. All right? So it's a very brute force synchronization construct. This is like expensive. You want to be really, really careful where you're using barriers. But when you need a barrier, you use a barrier because you need it. All right, so here we go. I've got a couple arrays, and I asked for a number of threads. Now I come into my parallel region. It's the SPMD pattern again. So I ask how many threads are there and who am I. And then I do my little trick to save the number of threads. Then I do a huge, big, ugly calculation. And it better be big and it better be ugly. And it's going to fill elements of the array A with that calculation. Now notice I then am going to call a function really big and ugly, okay, and it's going to use A. Now I cannot safely call that function until I know everybody has filled A, because I don't know inside that function how A is going to be used. So the only safe way to do things is to make sure that nobody calls that second function until everybody has finished the first. That's what the barrier does, pragma OMP barrier. And without going into the ugly details, let me just say, we take care of all the ugly memory model stuff so the visibility works. So basically, everything that happens before the barrier is visible to anything that happens after the barrier. You don't have to worry about that kind of magic. Okay? And if you do want to worry about it, then you should get help. Find a good therapist. All right. So now we have what I hope is going to be a really quick exercise. And this is a good chance for those of you who didn't quite finish the last time around to work to catch up. But what I'd like you to do is look at the Pi program, save the one you did before, but make a copy of a new one, and get rid of that array for sum, and instead use a critical section. So now you don't need to worry about false sharing. You don't have to worry about zero padding. You don't have to worry about declaring that array. All right? And get the program to work, but use the critical section. This should take no more than 10 minutes. Go for it. OK, so let's go on. Where are we? Oh, we just did this exercise. Yeah. OK. So remember, I had this version of the program with false sharing. And I went through and got rid of the array. I declared a sum locally for each thread. That's right there in the double sum. So now I did the partial sum into a local copy for each thread. And then after the loop, I put pound pragma OMP critical, and I did the multiply by step and accumulate into the final pi, and did that with mutual exclusion. So isn't that easy? That's like really easy. Gosh, what a wonderful design. So there's no false sharing because I don't have an array. It's just as easy as could be. And you look at the performance. It's interesting because I get the same performance as I did with the padded, pretty much. 1.87, 2 threads 1, 3 threads 0.68, 4 threads 0.53. So it works, and it gives me the same result as padded, but now I don't have all this weird, what the heck did you do that for with padding an array? I don't have to worry about this breaking as I move to a different architecture. So yes, you had a question.
Yeah, there's no brackets in the OMP critical, so is it?
Wonderful question. Thank you. OK, because I often forget, and I think I said this briefly, but I really need to hammer it home. OK? C is a block-structured language. A block is the open curly bracket or the closing curly bracket. But if it's one statement, you can leave off the brackets. So I only have one statement for my critical, so I don't need the brackets. But if I had 5 statements, I'd just put the brackets. But just remember, one line is logically equivalent to a block as far as the C programming language is concerned. So if it's a one line, I don't need the blocks. OK. So, so what do you think would happen if I did this? Did any of you try to do this trick? Yes, I'm glad some of you did. And furthermore, I'm glad you admitted it. That shows really great self-confidence. Just as a bit of comfort, I bet there's at least a dozen other people in this room that did it as well. So you have to remember that synchronization, thought of properly, applies an ordering constraint. When I have all these threads, now here we're going to get into some computer science theory, but this is one of these theoretical points that it astounds me that people who are old and experienced and should know better do not understand. So let me drive this home carefully. And this is the difference between concurrency and parallelism. Concurrency, when I have a collection of executing agents occurring and they are occurring concurrently, what that means is they are unordered. Okay? That's another way to say that interleaved comment I've said from the beginning. They are unordered with respect to each other. You do not know the order within which they occur relative to each other. Parallelism says they're happening at the same time. It doesn't say anything about ordered or unordered, by the way. Okay? These threads are executing concurrently. They are unordered. What a synchronization construct does is it puts an order constraint in. And the order constraint it's putting in is a happens before relationship. So when I put this mutual exclusion in there, I say that all those other threads, what they're doing happens before what's happening this time I'm inside my critical. And so if you look at memory models and people dealing with concurrency theory, everything comes down into what happens before when, because they're executing concurrently. But concurrency is not the same as parallelism. And the synchronization constructs are all about concurrency, and they're about putting order constraints. So in this code, given that this operation on X is so short in time, what am I basically doing to this loop by putting the critical in there? What order am I doing it? I've just basically serialized it. Yeah, I've pretty much serialized it.
So there is, when I did this, there was no difference when I increased the number of threads.
Yeah, if you did this, there would be no difference as you increase the number of threads. In fact, it might even go slower.
Yeah, on my laptop it's very difficult to see. But
yeah, it would probably go slower because you're getting a lot of overhead of threads just sitting here waiting for their turn. So what I want you to think about is you must put synchronization constructs in your code when they're needed. When you have to put an ordered relationship in there, you know, this update and write must occur before someone else tries to do an update and write. When you need to put it in there, you better put it there. But remember, you are potentially destroying your performance. So you think hard about synchronizing as little as possible. And of course, in this case, you would do it as little as possible by accumulating into a local so that the critical goes after the loop. OK, so enough on that. Oh, yes, you have a question.
So in this case, we don't actually need it to be ordered. We just need it to be one at a time.
Which implies an order. But you're right. I'm not specifying a total order. I'm just specifying a happens before relationship, but not a total order. You are correct. OK. There is, by the way, an OpenMP construct that lets you imply a total order. But it's not in the Common Core because, frankly, you shouldn't use it. OK. Let's talk about parallel loops. Here we are, halfway through an OpenMP course almost, and this is the first time I've said parallel loops. Isn't that weird? Those of you who know something about OpenMP. OK. So in OpenMP, if you're going to create threads, you do it with a parallel construct. That's how you create threads. There are another class of constructs in OpenMP that share the work between threads. Remember, with a parallel construct, what's in the sequence within the structured block, every thread will execute. What a work share construct does is it says, take this work and split it between threads. The work share construct that people use all the time is a loop work sharing construct. And in the C programming language, that would be pragma OMP4. Okay? So I need to create my threads. A pragma OMP4, if it's not inside of a parallel region, doesn't do a thing. You've got to have threads to split up between. So pragma OMP4, create a bunch of threads. I'm sorry, pragma OMP parallel, create a bunch of threads. Pragma OMP4 says for the immediately following loop, so it applies to the immediately following loop, split the iterations of this loop between the threads. Now, OpenMP, because we try to make the default behaviors safe, in OpenMP, we recognize that there is no logical reason you would ever want the loop control index to be shared. That just doesn't make sense. So we protect you, because we're wise, by making that private to each loop for you. But it's only that loop. That's, let's say I have another nesting of loop. Then you're on your own. Okay? So now I'm going to call that function neat stuff, and the runtime system will take care of splitting it up between the threads. Now, at the end of the work share construct, and this is true for all of the OpenMP work share constructs, we're going to see one more before we're done here today. But at the close of that construct, which is going to be the end of this parallel loop, there's an implied barrier. And that's once again because in most cases, we want to make it so that by default, you're likely to do the safe thing. And usually at the end of a loop, you want to use what you did in that loop. So the safe behavior is we're going to put a barrier there. Now to motivate this, let's look at this wonderful, simple little code. I'm going to do a vector add. A of I equals A of I plus B of I. And there's the serial code at the top. Then in the middle, I do that block structured trick that those of you who did your Pi program have done again and again. So I've done all of this. And by the way, okay, all of that to split it up. Or I could just do this, pragma OMP4, pragma OMP parallel, pragma OMP4. Pretty darn easy. So which of those would you rather do? The funny thing is, I remember way back in the dark days of 1996, when we started talking about all this, there were people really saying we should just stop here. Because really, you don't need, this thing here with pragma OMP4 is just lazy. We're just rewarding you to be lazy. All we really need is create an easy way for you to make threads. Needless to say, we ignored that silly person, and we went on. It wasn't me. There are other things, other battles I fought and lost, but that's not one. So yeah, that's much, much easier. Now, most of my colleagues at Intel hate the way I teach OpenMP, but I'm right, they're wrong. They go straight to this. All right? They like lesson number 1, pragma OMP parallel, pragma OMP4. Off you go. All right? My problem with that is then you don't realize that there are threads underneath. You don't realize that there's data that's coming from outside the block and there's data inside the block. You don't have a good deep feeling for how threads in general work, for the interleaving, for the data races. And if you're going to be a competent OpenMP programmer, you need to know that. So this is why I always start here and get you to deeply understand all the ickiness of threads, because they don't go away. All of the issues are still there. I'm just getting the compiler to do more of them for you with this. But it's important for you to understand that. Now, when I have pragma OMP parallel and then pragma OMP4, I'm telling the runtime system, you are wise and good, and you will figure out the best way to distribute those loop iterations. Okay? If any of you have spent any time at all in high-performance computing, you know that's usually a formula for disaster. Okay? You know an awful lot more about what's happening inside your loop than a compiler will ever know. So we have a way for you to tell the compiler information about the schedule. And there's more than this. These are just the ones that are used all the time. Okay, so I can have a clause called a schedule clause. So it would be pragma OMP for schedule. And then the schedule can be either static or dynamic. As I said, there's a few more, but they're rarely used. So let's just talk about static and dynamic. And there's an optional chunk size. OK, so let's start with static. So with a static schedule, pragma OMP for schedule static, I'm saying break the iterations into a number of blocks equal to the number of threads, give one block to each thread, and it's OK if the last thread is a different number of iterations. So what I did here on this slide, if you look at that middle parallel region, that's basically what pragma OMP for schedule static does for you. All right, that's pragma OMP schedule static. Now, a little interesting trick. I can do pragma OMP for schedule static and then a chunk size. And let's say I chose that chunk size to be a small number corresponding to my cache utilization. And of course, this depends on the reuse and depends on the code. But I'll put 8 there because I know that I can fit 8 floats into my cache lines. It depends on your cache reuse and your algorithm. But I can put a small number there. Okay? What that chunk size says is take the iteration space of the loop, break it into consecutive, contiguous iterations of size chunk, and now deal those out to the loops. Okay? So now I'm taking, maybe I have 1,000 loop iterations, let's say a chunk size of 10. So now I have 100 blocks of size 10. I'll give a size of 10 block to one thread, size of 10 block to the others, and it'll go round robin, so I'm dealing it out like a deck of cards. But now I'm giving a block to each thread that is optimized, if I pick it right, for the size of the caches, and giving it a bit more work to do as I do the work. Turns out in many cases this gives me nice load balancing as well. We haven't really talked a lot about load balancing. But for the Pi program, every iteration took about the same amount of time. But in reality, when you start dealing with real codes, some iterations can take much, much longer than other iterations. If I give each thread one huge block, I've done nothing for load balancing. Now I'm just sort of trusting to luck. But many, many codes will load balance very nicely if I just get lucky with the small chunk size and distribute it. So that's the most common that you see is pragma OMP for schedule static with a modest sized chunk. That's what you see most of the time. Now, there's another case, though, and that is where you have loop iterations that you just can't predict. You could have one that's 5 minutes. You could have one that's an hour. You have absolutely no way of predicting. I run into this a lot. So where I've done a lot of my own work in my career is in molecular dynamics. I wrote some of the very first parallel molecular dynamics codes. And because of that, I did parallel molecular dynamics forever. Okay? That's a classic instance of something where, as you think of a protein folding, when it's in a tight neighborhood with a lot of other atoms, its updates take a long time. When it's in a sparse neighborhood, they take very little time. As the molecule flops around, your neighborhoods change. So you have no way of knowing ahead of time how those iterations are going to distribute. So for that, we have the dynamic. So pragma OMP for schedule dynamic says, take all those loop iterations, put them into a queue, and hand one assignment of work to each thread. When it's done, it'll go to the queue to get the next one. So now I have dynamic automatic load balancing occurring for me. And the chunk size says, instead of breaking them into chunks of size 1, give me blocks. So if I have chunk size 10, I will create blocks of the iteration space in size of 10. I'll give a block of 10 to one thread. When it comes back, give it the next block of 10. All right? So the default on static is 1 chunk per thread. The default on dynamic is 1 iteration per thread. So they have different defaults. The chunk size does the same thing. It's for determining the number of iterations, blocks. Now Static, gosh, I've talked way too long. I need to come up with an exercise that shows the difference between dynamic and static. This is a missing exercise. But at any rate, so dynamic I use in unpredictable, static I use when it's predictable. Static, all of the overheads at compile time, because I can create one-to-one functions that determine the iteration space. So I compile in all the scheduling overhead. Dynamic, the scheduling overhead is runtime. So if I can do it with static, I'm better off. But if I have to do it with dynamic, that's what I do. So those are the two major options people play with. Now here's another thing. Pragma OMP parallel, do something, Pragma OMP 4. What a pain to type that much. Wouldn't it be nice if I could just put them together? Wouldn't that be great? Wouldn't it be really smart if we had thought of that? Oh, we did. So Pragma OMP parallel 4. All right, that works. And so what most people do, those two are equivalent to what you see the code up there. So what most people do when they look at their code is you look at your code and you find the compute intensive loops. Then you make the loop iterations independent so they can execute in any order. And then you put the appropriate Pragma OMP parallel 4. So this is what people do. So if you look at this loop here, this loop has a loop carry dependence because the way I'm defining j, right? J plus equals 2. All right, so I'm going to have to change it so I compute j, int j equals 5 plus 2 times I plus 1. So now I've just transformed that loop so that it is no loop carry dependencies. It can execute in any order and give me the right answer. And then I just put Pragma OMP parallel 4 in front of it. Done. So I would say that most people, this is how they use OpenMP. It frustrates those of us at a place like Intel to no end, because there's often a lot more clever and performant things you can do if you go further than this. But this is what most people do. Just find the big loops, make them independent, Pragma OMP parallel 4, done. So that's it. So if you just learned that, you're done. Well, there's a little more. Because you often come up with this case where you have an accumulator. Like, oh, I don't know, let me think. Imagine a numerical integration, maybe to compute pi. You folks know about this, right? You're accumulating a value. So there has to be a way to deal with that. And there is, it's called a reduction. So here is exactly what the reduction does. And this is important. There's a clause, reduction. You have an operator, a colon, then a comma separated list. For each variable in that list, it'll create a copy of it private to each thread. It will initialize it by the identity of that operator. It will then, anything will happen, it doesn't care. The code inside the block will do whatever it wants. Then when it's done, it will combine the local copies into a single value using that operator. Then it will combine it with the original value, the global value that existed before the parallel construct, and give you the final answer. So those are the steps. So simple case is just this right here. I want to do the average. OK, Pragma OMP parallel 4 reduction plus colon av. That's it. That's done. What could be easier? And most people, it's just the plus you use. I mean, it has to be an associative operator. But let's just say there are other operators you can use. You know, multiply, negative, min, max. There's some that are Fortran only, some that are C and C++ only. You know, just worry about the plus for now. Just know you can look up these others. And we don't talk about it in the Common Core, but in C++ and where you're having classes and object types, you can define your own reduction operators. So there are user-defined reductions. We won't talk about them, but you can look it up. All right, so it's lunchtime. And I like to leave you with an exercise, because some of you are having so much fun that you're going to rush off to lunch, eat as fast as you can, and then dash back here so you can do this exercise. All right? So the exercise is very simple. Go back to that original pi.c program. All right? And parallelize it. And your goal, and only use these operators, cheaters. I'm looking at you, cheater. Only use these. Okay, try to change as few lines as possible in the original code as you can to create a parallel version of it. You know, remember, what's interesting, if you've already done it, Run it for 1 threads, 2 threads, 4 threads for each of the versions you've written. And just jot down the performance and compare them. So for those of you who've already done it, just collect that data. Notice up there, git clone github.com, TG Mattson. You know what? Every single one of you should just open up a window on your laptop and do that. Okay? That will get you a copy of the slides. That will get you a copy of all the exercises, all the solutions, including that learning C file. You should just have this on your laptop to take back with you, because you notice when you get back to your home institution, you're now going to be the OpenMP expert. And so everyone there, when they say like, oh my goodness, you've been through one of Tim Mattson's OpenMP classes. Can you teach us OpenMP? So, it'll be really handy for you to have those exercises, because then you can just sort of say, yes, it was wonderful. Let me teach you. So I urge you all, just do that git clone and just do that at the top. Even if you're going to do all the exercises on the systems, Cooley or Vesta, just have it on your laptop. Yes?
Reduction is generally for scalar variables. Is there a way that you can implement it on, say, a vector or an array?
So the question is about reduction, and as I've shown it to you, it's just for scalars. And as reduction was originally created, it was just for scalars. And I forget exactly when. It might have been OpenMP 4.0. So it was fairly late in OpenMP's life, because today we're at 4.5. But it was around the 4.0 time frame that we added reductions over array sections. So now you can do reductions over arrays. We don't cover it in the Common Core, but there is reductions over the arrays. Now let me say something about these slides here. You have it as a PDF. If you've taken time to look at it, and don't bother right now, but I just want to say, it's basically the outline of a book on OpenMP. So it talks about array reductions. It talks about a lot of stuff that we are not going to cover. So there's a wealth of information in here, even that we're not going to go to. And actually, right now, I am writing a book with these slides as the outline, so that there's a decent book for learning OpenMP from. But I just mentioned it because there really is a lot of good stuff in here for you to study on your own when you leave. Because obviously, in one day presentation, you're not going to learn all there is to learn about the OpenMP, even to the Common Core. So there's a lot of extra material that you can go in and work with. And it's really awesome and really cool and good, and you should. Because OpenMP is like one of the greatest things ever created. It's utterly amazing. Right now, if you knew OpenMP and MPI, you pretty much would be ready in supercomputing, if you look at most systems. GPUs are filtering in, and so you probably need to know OpenCL or CUDA, but there's not a large number of programming models you really need to know to get up and running. But it's going to change. Over the next 10 years, everything's going to switch to C++, whether you like it or not. And then we'll have higher level abstractions, and it'll be very, very different. But right now, it's still OpenMP. All right. So let's look at my solution to this incredibly complicated exercise. Because after going through all the ones we did before, this one's pretty darn easy. So, pragma OMP parallel to create the threads. I still need to give each thread its own copy of x, so I declare double x. Then I do pragma OMP4 reduction plus sum. Done. That's it. Isn't that easy? Now, there's a couple little things that I find interesting to explore. Why did I do this? Pragma OMP parallel, double x, then pragma OMP4. I bet a lot of you did pragma OMP parallel 4 reduction, and then you did the double right there, right? And let me tell you, good. That was the right thing to do. It would be interesting to do a survey, but I could probably figure out who's old, C89 old, and who's young, C99 beyond. Because in the old days, if I put the double right here, a compiler would allocate that space inside the loop. And therefore, you would never do that. It would make you throw up to see someone declare a variable inside the loop. All right? And therefore, I just can't bring myself to do it. But I need to grow up, because any decent compiler, even a bad compiler today, if you put the declaration inside the loop, it will promote it around the loop. So, that would be a correct decision, to do the pragma OMP parallel 4 and then put the double in there. So this is just a sign of my old age. OK, so if you look at my results, I get a little bit more overhead on my loop version of the program. I don't know why. I don't care. But you see, I get reasonable speedups with the loop. And it's definitely simpler code. It's definitely easier to maintain. It's definitely closer to the serial code I started from. It's just superior in every way. So this is a great way to do it. Any questions? None. You have, oh, yes.
So when you're only using one thread, it gets greater and greater, and that's because of overhead.
What gets greater? Oh.
When you're using one thread, it kind of rises a little bit.
Yes. You notice with one thread, it was 1.83 seconds. And then as I added threads, it's a little bit greater, yes. So there's overhead in the environment setting up for the parallel computation. So,
you don't need it.
Pardon?
Like, you don't need it after all, because you're only using one thread.
If you're only using one thread.
There's no use in the...
Right. Now, there's actually a real deep angle to what you're bringing up. I haven't had time to look at all the other lectures that have preceded this one. Has someone talked to you about how to lie with speedups? Okay. So there is a classic paper in HPC by David Bailey on how to fool the masses with benchmarks, or the 12 top ways to fool the masses with benchmarks. It is a must-read. It's an old paper, but it's basically how you can, by tweaking things, you can manipulate the view of the data. So a classic one that I see a lot today that just pisses me off is the GPU people, the NVIDIA marketing people. Now, let me just be clear, because this is being videotaped. No, let me say, I'm unusual at Intel in that I love GPU programming. For the right sort of algorithms, I thoroughly enjoy programming. I usually do it in OpenCL, but I enjoy CUDA as well. I have tremendous respect. Seriously, I'm looking into the camera to make sure. I have tremendous respect for my technical colleagues at NVIDIA. The NVIDIA marketing people often piss me off, okay? Because they will manipulate benchmarks to lie, and they don't need to. They have a fine product. They can stand on the merits of their product with a technically honest way. They don't need to lie. But one way to lie, for example, is when you do a speed up. You'll see how this is coming around to your question. When you do a speed up comparison, what is the ratio? So speed up is measured as the ratio of, usually, the best serial algorithm running on a serial core to the best parallel algorithm running on a parallel core. What the NVIDIA marketing hacks, who should go crawl under a rock, often do, is they will run the code like with Python, with zero optimization on one core of a CPU, and then compare it to a CUDA program running on a Volta 100, where someone has gone through and by hand implemented a beautiful, elegant CUDA solution. And then they'll say, look, it's 1,000 times faster. It's like, come on. For the right algorithms, sometimes it's 2 to 3 times faster, sometimes 10 times faster. I mean, for the right algorithms, there are definite benefits to the NVIDIA parts. But depending on the algorithm, sometimes there's benefits to the CPU parts. You have to tell based on your own particular benchmarks. OK, good. So I want to be really careful here. But at any rate, what you compare against is really important. So as you can see, in this program, if I define speed up relative to my parallel programming run with one thread, I'm going to get better speed ups if I do the honest thing, which is comparing one program running on one thread with a serial algorithm. Because that number is 1.83 seconds. And I should be comparing all of my speed ups relative not to the 1.86, or in the case of the pi loop, the 1.91. I should be comparing them all to that 1.83. The honest way to evaluate speedups is whatever you're comparing against, you want to compare against the best implementation of what you're comparing against. So parallel runtime compared to the best serial algorithm is what you should do. And you can see in this case, even for this silly little simple program, there is significant overhead in setting up the extra memory and setting up the thread pools and in loading the extra dynamic libraries. I don't know all of the pieces of it. But you know, 1.83 versus 1.86, that's a significant amount of time. And so think hard when you do the speedups, so what you compare against. Because you don't want to be on a video of Tim Mattson criticizing you, like I just did the NVIDIA marketing folks, because you lied about or were dishonest about the speedups you compare against. All right. One of these days, I'm going to get fired. Oh, I have some great stories where I came close. So, all right, I want to talk about, there's a lot on this slide, but it has a very important concept in terms of thinking about programming in general in parallel. So remember, overheads clobber you. And you have to be very, very careful where you introduce overheads. And there are few things you can do that add more overhead than a barrier. So you want the ability for a work share construct, which implies a barrier. So it's important on a work share construct, you have a way of saying, look, system, I know enough about my algorithm. You can get rid of that barrier. You don't really need it. That's called a no-wait clause. And on any of the work share constructs, of which you only know one so far, but you can put a no wait. Let me walk through, because this is a case showing you where you would use a no wait. All right, so here we go. I have my 3 different arrays. They're big old arrays, A, B, and C. And so I have my parallel region, pragma OMP parallel. All right, SPMD program, guys. I get my thread num. All right, now I'm going to call a big calculation, and I'm going to populate the result in A. And then I'm going to enter a loop where I use A. So you know, if you kind of think about it, what do I have to put before I enter that loop? Barrier, it's up on the slide. Barrier, come on, you got to interact. I know we're after lunch and you're all kind of like diverting blood to your stomach to digest, but let's interact, right? So I need to put a barrier because I need to make sure before any thread starts executing this loop that everyone is finished with A. And let me emphasize, there is not a barrier on entry to a work share construct. There's a barrier implied on exit from a work share construct, but not on entry. All right? Now, I won't go there. I'm sorry. It's really hard to not drop into little technical asides. So at any rate, no barrier on entry. So I have to put the barrier here. Now I enter the loop, and I'm going to do a big old calculation, and I'm going to put the result in C. Now I look ahead of my program, and I notice that I'm now going to enter another loop, which is going to use C. Therefore, I need to have a barrier so everybody is finished before anyone goes into that loop. No problem. There's an implicit barrier at the end of this loop, right? Because a work sharing construct by default implies a barrier because that's the safe behavior. Now I get into the next loop. And I'm going to do a big old calculation and put the result in B. And then following that loop, I'm going to do another calculation and put the result in A. And then I come to the end of the program. Notice the calculation on A does not use B. So I don't need to wait for B to finish before I do this calculation. Right? So there's no reason to put that barrier there. And barriers add a lot of overhead. Anytime a thread is waiting on another thread, you are adding overhead. And according to Amdahl's law, you've all learned about Amdahl's law, right? Yeah, right? Okay, good. Think about exascale and then think about Amdahl's law. Yeah, right. Okay. At any rate, yeah, I'm going to run on 1 million cores and have less than 1 part in a million overhead. Yeah, right. Good luck. Good luck with that. Oops, I'm on video. I love exascale. I think it's a good thing. Okay. So there is no reason for you to put a barrier before this calculation. So I put the no wait. Then there's a barrier at the end of the parallel region. There's no way for you to turn that off. Remember, the threads logically join at the end of that region. So it doesn't make sense for any thread to go on. Of course, there's only one thread that's going to go on, and it's thread number 0. There's no reason for that thread to go on until everyone finishes. So there's no way for you to turn off this barrier. But I can turn off this barrier with the no wait. Okay? So does that make sense? And what I also want you to see, though, is the reasoning I went through in thinking about that code and thinking about where I truly need barriers and where I can get rid of them. Because that kind of reasoning is important whether you're programming in OpenMP. I mean, that's just general parallel programming. You know, I have to go through the same kind of thought process when I work with MPI. So this is just good parallel programming practice. Yes?
What if you really did need a barrier, but you had said no wait?
What if I really needed a barrier there and then I said no wait? Okay, wonderful. Let me be abundantly clear. OpenMP is an explicit programming notation. What you tell it to do, it will do. And it will not protect you from stupidity. Okay? Now, this is a big topic of debate when we were creating it. You know, we could have defined it to try and protect you from stupidity. The problem is when you do that, you end up having to play it safe and you sacrifice performance. So if you needed a no wait and you did, like let's say you put a no wait here, you would have a race condition. Your program could give you a different answer depending on how the threads were scheduled. You would have no warning that that was the case. You'd be getting wrong answers and you wouldn't even know it. It'd be a disaster. So every time you put a no wait into a program, you need to really inspect it closely because the compiler will not help you decide if that's something you should have done. And it'll just go right on ahead and do it, you know. Yes, master, I will drop that barrier and go right on ahead because you obviously know what you're doing. Huh, right. Well, you know what you're doing. I mean, I may not. Okay. Okay, here comes a really big part that kind of finishes the traditional heart and soul of OpenMP. And that's the data environment. We've talked about creating threads. We've talked about synchronization, so ordering loads and stores, providing ordered blocks of code for mutual exclusion. We've talked about parallel loops. You know, this is all the bread and butter, heart and soul of OpenMP. What we haven't talked about is how to modify the data environment. So that's where we go right now. And this is a big part of what you do when you're actually programming with OpenMP. So OpenMP is a shared memory programming model. Just like P threads, just like in Java, just like in C threads. It's a shared memory programming model. And so variables declared in memory that are visible across all the threads, which is pretty much most variables coming off the heap, anything declared in front of the parallel, you know, they're shared by default. And then there are global variables that are shared among threads. So in Fortran, yay, Fortran, right? Okay, in Fortran, your common blocks and module variables and save variables are shared. So even if wherever I'm declaring a common block, it's going onto that process portion of the memory that is shared across threads. In C, a file scope variable. Okay, so for those of you who are not C programmers, you know, if I declare loosely, if I declare it before the main, that's a file scope variable. It's visible to all the functions in that file. File scope variables are shared by default. Or if I declare the storage class of a variable as static, it becomes shared. If I have dynamically allocated memory, which we're not going to deal with in any of our exercises, we're just going to mention it. You know, if you use a malloc or an allocate in Fortran, okay, now I'm getting dynamically allocated memory. That's coming off the process heap that belongs to the process. It's shared to all the threads. It kind of makes sense, I hope, if you think about it. Okay? But if the data is coming off, and now I'm going to slip into a little operating system terminology here, the thread stack. Okay? When a thread is created, remember, you have a process that the operating system creates for running your program. That process has a block of memory, usually managed as a heap, that is visible to all the threads. The process is a container that holds memory that are managed by the operating system, and it holds all these hooks for getting into the system. Okay? Anything that executes is in a thread. So they're going to create a thread, and it sees all of the resources of the process. When a thread is created, it has its own program counter, its own little view of the register stack, it has a little piece of memory that's local to it, that's usually managed as a stack. Okay? That's private to the thread. When I call a function, there's a stack allocated for the function. This is a temporary block of memory the operating system manages for you. So variables that are called on either a function stack or a thread stack, or if you don't like the word stack, just think little bit of private memory that's local to the function or local to the thread. Those are private. Okay, so let's walk through this example and make sure in excruciating detail you understand it. And this, as you will see in a moment, is a head nod slide. You'll see what that means. All right, here's a program. I have double where I declare an array. Then I have my int of main. Then I have an index that I declare inside main. Then I have a parallel region that calls work, where I pass in index. Now I have a function. And this is a piece of C notation some of you haven't seen before. Extern is telling the function, look for a file scope variable, a global scope variable of that name double. That's what that extern means. All right, so I'm looking for this global scope variable. I'm declaring it extern. I go inside work where I pass in the array. That little asterisk there says I'm passing in a pointer to the reference to the array. A little bit freaky, but don't worry about it. It means I can reference that array inside the function. Then I'm going to declare an array inside the function, and I have a static inside the function. So you see, I have all these different variables in these short little code snippets. Okay, let's walk it through and make sure we understand. So A and index were declared prior to the parallel region. They are visible to everyone. Because count was declared static, so its storage class was explicitly declared as static, it is of global scope. All right? So all the threads can see it, and they're shared. However, temp is declared inside the function. It goes inside the function stack. It's private to every thread. All right? So if I look at the execution, I have these as global and a temporary for each of the functions. And then at the end, the temp goes away as it goes out of scope, and I just see A, index, and count. These are the default sharing rules of OpenMP. Does this make sense? You have a question? Yes?
So what if I want to dynamically allocate something within a parallel region?
Then I would declare the pointer inside the parallel region. If I wanted to dynamically allocate memory inside the parallel region, I would declare a pointer inside the parallel region, and then I would allocate it. It's still in the heap. It is still shared, but I have a unique pointer to each piece of memory. But it's still going on that heap. So I could, if I was wicked and really nasty, I could do that, and then I could jump and see that memory from another thread. It's very, very bad programming practice. But yes?
So the static variable count is available everywhere because it's declared as a static. But if I tried to reference it before work was called, would that be okay?
Great question. He's talking about the static int count that I said is of global scope. And this is a subtlety, and I'm going to apologize in advance for proper computer scientists, because I'm sure I'm going to get the jargon wrong. Because I am a theoretical chemist and molecular physicist by training, so I get kind of hung up on some of the low-level jargon. But here we go. The storage class of count is global. All right? It is available to all the threads. But the visibility to count is inside work. I can only get at it inside work because it's declared inside work. So I need to, so if I could find some back door that could look at that memory address, sure, I could see it anywhere. Because that address is in, this is why I go on and on about the structure of a process and that you have a heap. Okay? Because it's static int count, it sits in an address in the heap which is visible to all the threads. But within the managed namespace of my program, it's visible inside work. So I have to do something to make its visibility outside work. All right, now, before I go further with any questions, though, I need to make sure, do you all understand this slide? I want to see a head nod. Okay?
So is there something equivalent to the static in Fortran?
There is, but I don't know what it is. I mean, you know, it has been so long. I haven't done significant Fortran programming since 1999, maybe, 98. It's been a long time. So, but yes, there is an analog to that. Okay, and we will come to your question. Any other questions on this slide? Yes?
Are they going to have separate pointers to that index array when you pass the function there?
To which array? I'm sorry, huh? What?
You are calling the function work, and you said that the function parameters are local and they are replicated, right?
So index is an array. I'm passing that array into work, which takes a pointer. So all of the threads see that same pointer. That's a shared variable.
So one of them updates this address. So all of the threads are going to see that address?
Yes. All the threads are going to see that same address because index is shared. Which means inside work, if I'm doing writes into index, what had I better do inside work? What?
Critical.
Critical, yeah. I better synchronize it. So what I would do is I'm going to do a bunch of stuff, and then when it gets time to actually do the update to work, I would put a critical there, because it's visible to all the other threads. And you are not allowed, you are specifically forbidden, and I actually think this is a mistake in the definition of the C and C++ programming languages. I don't know if Fortran does the same thing. I would expect it does. Because they say that if you have a data race, you have unordered mixtures of reads and writes to the same address, it is an invalid program. The problem is there are times we want to do that, but at any rate. So if I didn't protect the updates to index inside work, it's an invalid program. And so you have to do that.
Okay, so they're going to have a single pointer that's shared among all threads.
That's right. A single pointer that is shared among all threads. Absolutely. There's a question behind you. Oh, I thought you raised your hand. You didn't. Okay. You.
Okay. Is there a problem if there's a data race, but they're going to write the same thing?
So I talked about that earlier, but this is a subtle but important point, so let me address it. He asked, is it a problem if there's a data race? So remember, data race means you have reads and writes, or you have writes to a single address occurring from multiple threads, and they are not ordered. That's a data race. In a data race, a program that has a data race is an invalid program. That is the official definition in ANSI C and ANSI C++, and OpenMP echoes that, and OpenCL echoes that. It's pretty much what compiler people say today, is that a data race means the program's invalid. Now, if I'm writing the same value to an address, I am still a data race. I am still violating that rule. Now you get into the low-level details of the memory model. On an Intel x86 processor, we do something called relaxed atomic writes. We do that by default. So on an Intel system, that's still the correct program. But I'm just telling you, it's evil. You should never write a program that only runs on one architecture. You should always write it assuming, yeah, but what if tomorrow someone runs on a Power, an IBM Power 8 or an ARM? So you always have to write, and on those memory models, they're different, and I think there you could get garbage. So even if everyone's writing the same value, you synchronize and protect it. Yes?
So when you want to make sure that you don't do that, but you also don't want to pay too much in performance, what could you do? So in an example, if you have local small matrices you computed on a thread, and you want to write those results to a global matrix, and there's going to be a few overlaps that write the same values to an index, but it happens very rarely. But now, if you do would you try to split that and write the ones that you know that are safe to write first, and then only do the critical on the ones that might overlap?
Let me build on that, but not spend too much time. Remember earlier when I brought up synchronization, I said I could talk for 2 days about this topic. These are one of the things we talk about, all right? When you have lots of writes happening from lots of different threads, if you're not smart about what you do, you can destroy your performance. And there are many things you can do in OpenMP, in any multi-threaded environments that we're not talking about because you're really getting down into a lot of details. But yes, you organize it so that you do the safe writes. You try and overlap so that while you're waiting on one unsafe write, you're doing the safe writes. There are locks which are described later on, which depending on how fast we move this afternoon, we'll get to. So there are features in OpenMP for dealing with this. So yeah, this is a big part. When you get beyond the basics of multi-threaded programming and get to advanced multi-threaded programming, those are exactly the sorts of issues. Is how do you minimize the synchronization overhead? And there are just a host of tricks you can do. And if you are a really twisted human being, like the sort of human being I'm not sure I want to spend a lot of time with because you're just too weird, learn about the C++ memory model and all the weird things they added, acquire and release semantics, and there's a host of these low-level details, and they're all built in for exactly dealing with those situations of how do you just have the minimal overhead when you have these conflicting writes that you just have to manage. Clearly, I went on and on and on about the default storage rules because now I want to talk about how to change them. And we have clauses for changing them. And this isn't all of them, but this is most of them. So each one of these clauses, you can put these on a parallel. And you can put them on a parallel, you can put them on a for. So you have a shared, and then a comma-separated list, private, a comma-separated list, and first private, a comma-separated list. Shared is what you have by default. So really, you don't use that much. But shared just says, and all of these, by the way, let me be really clear. You have an OpenMP construct. There are a set of variables that exist before that construct. We'll call those the original variables. Now I'm going to enter the construct. Okay? Now the construct, if I enter it, it's by default, most of those variables that existed before the construct will be shared inside the construct, right? And all of these shared private, first private, they change the behavior of those variables inside the construct. So shared is just the default. It's just, yeah, you know what? This is what it does. So the ones you really use are private and first private. What private says is, remember, you pass in a list of variables. That's what that list on the slide means. What it says is inside the construct, create a variable with the same name as the original variable in the list, but don't initialize it. That's what private does. I have examples coming up. On this slide, I'm going to explain them, then I'll have examples. Then you're going to get a fun exercise with this. Okay. First private says, create the variables. So I'm going to create each variable in the list. Each thread's going to have a copy of the variable with that name. But first private says, initialize it with the copy of the original variable. That's what first private does. Okay? Now, there's one other. You can change the defaults. And there are multiple ways. If I could go back in time, I would change it so that the only thing there is default none. But let's just say that the only thing there is default none. There's a default shared and default private. And all it just says is we're just changing the default. What you have now is default shared. You enter a parallel region, it's as if you had everything shared. You do nothing, that's what happens. What default none says is you must explicitly state the storage class of each original variable as you cross into this parallel region or into this for loop. So I could have default none, and then I have to go, oh, private X, first private this, shared that. So remember we were talking about the dangers of a data race, the dangers of accidentally thinking something's private when it's shared. The easiest way to prevent that is to always put a default none on your constructs. So now you have to explicitly go through. You Python programmers will cringe because Python programmers, for some reason, don't like declaring variables. It's just really weird. But for us C programmers and Fortran programmers, it's just the natural thing to do. Actually, yeah. So here's some examples, which will make all of these really clear. So here's a program. It's wrong for other reasons. Don't worry about it. But I'm going to show you the loop. So here I have a pragma OMP parallel for, and I say, inside the loop, I'm going to update a temp. So I go private temp. So the original variable is the one that existed before the construct. So I have int temp equals 0. That's the original variable. Because when I need to refer to the one before the construct and inside the construct, that's the jargon I'll use. The original variable is the one that existed outside the construct. So now I come in the construct and I said private temp. So now inside that construct, each thread, not each loop iteration, each thread will now have its own copy of a variable called temp. OK? That's really great. So now I go temp plus equals j. The problem here, though, is temp was not initialized. So this is incorrect, right? Remember, private says create the variable. It does not say to initialize it. So it's an uninitialized variable. And in C, that's a bad thing. All right, now I get to the end of the construct, which is just this loop. And I print temp. And because that private goes out of scope when I leave the construct, what do you think I print? 0. Okay? So that's private. Now the way I would fix that is with, oh gosh, do I put that now? Oh, I do. All right. Here is a bad human being who wrote some code that they should be punished for. But here we go. Because the language says you can, because the C language says you can do this, you have to be prepared for this. OpenMP says if you do this, it is an invalid program. So you're not allowed to do this. All right, I declare a file scope variable temp. By the way, file scope variables, globals, are generally bad form in C. Sometimes you have to use them, but you need to minimize when you use them in C. So I declare a file scope variable temp. Now I have a function, and inside that function, I initialize temp. Now I'm going to enter a parallel region, pragma OMP parallel, and I declare a private temp. Then I call work. So now we go into work, and work I tell it extern int temp. So I'm telling the work function, expect a global scope variable. And then inside work, I'm going to assign a variable to it. Which variable temp gets assigned that value 5? What the compiler writers say is there's absolutely no way for them to know if it should write to the file scope variable, global scope variable, or if it should write to the masked temp inside this structure. that temp there that masks the global scope. The compiler cannot know where to write that variable. It is so hopelessly confused, it will just roll over and die. So when a compiler writer finds something that's hard, they do the ultimate cop-out. They say, this is an invalid program. We don't have to do anything. You guys are screwed. So don't do it. It's an error. I got to be careful, because I'm not sure that compilers are guaranteed to warn you of this. I have to be careful, because when something is defined as an error, that means the compiler is required to detect it. I'm not sure if this is defined as an error in that context. I'm not sure the compiler is guaranteed to detect this. But if you do this in a program, it is an invalid program, just like a data race. It's an invalid program. Don't do it. All right, here we go. First private. Oh, yes. And speak up really loud, because I have very old ears.
In the red part, why the temp is the copy?
Why is the temp? So let's walk through this, because it's very important. OK. I should probably say which version of temp. I think you're reading more into the word copy. I have found in my life that when people are confused, there's a chain of definitions that usually are confusing them. So let me be very, very clear. What is a variable? A variable is a named address. Okay? We human beings will get really frustrated very quickly if all we carried around with us was addresses. So a variable is a way for us to take an address and give it a name. So when I do global scope variable temp, I have an address on the heap, and I'm giving it this name temp. Then I created a private variable here, which created a new variable called temp. And there's now an address that the variable temp points to. All I'm saying is that when you get to this statement, there is no way in general for a compiler to know which address you meant for it to update. That's what I mean by my statement, unspecified which copy of temp. Okay. So the compiler has no way of figuring out which address you're telling it to update. And so it's illegal. Or not, it's unspecified. What I'm going to suggest, if you're still looking confused, I'm going to suggest we talk later, because I have to get the group to the exercise. Is that OK? That's the second time I've done that to you. That is really bad. Shame on me. Bad Tim. Let me talk about first private. So what first private says is it says, do the same thing as private, but initialize it with the copy from the original variable. Pretty straightforward. So now here I have an increment, and I initialize it to 0. The original variable has value 0. I'm going to enter my loop. And now everything's very well formed, because I'm saying give each thread its own copy of increment and initialize it to 0. So now this is a correct program. OK? It's a very simple concept. Private doesn't initialize, it just creates a local copy for each thread. First private creates a local copy and then initializes it. All right, here comes a test. Consider a program. And then that program, I have variables, a equals 1, b equals 1, c equals 1. Now I'm going to enter a parallel region. Pound, pragma, OMP, parallel, private, B, first private, C. So I want you to think in your own head, OK? As I enter into that region, are the variables private or shared? Then I want you to think about what are their values inside the parallel region when I first enter that parallel region, and what are their values when I get outside. OK? So think about it. I should bring my guitar, and I could play the little Jeopardy song, you know. I'd sing it, but you wouldn't like that. But I have a guitar in my room. I should just bring it and plug it in. And all right. I bring a guitar with me everywhere I travel. All right. So A, because we didn't change its storage class with a clause, is handled by default, which means it's shared. So every single thread is going to see its value 1 at the start. B and C, because I modified their storage treatment, I made them private. But B, because I used just private, is uninitialized. Whereas C, because I made it first private, is initialized and equal to 1. When I leave the program, B and C revert to their original values because the private copies created go out of scope, and so all that's left is the original value. And A has whatever value was computed inside the region, right? Does that make sense? Yes?
So is there any benefit of using private over first private? Because I like any case that I can think of right now, like first private would probably work always, right?
So the question was, is there any benefit for private over first private? Now, you know, I made my jovial, it was jovial, really. I made my jovial comment about exascale computing earlier, and it really was jovial. But there's a serious tinge to it, okay? I want all of you to get in the habit of doing everything as low overhead as possible. Because when you start talking about scaling to large numbers of threads, little itty-bitty things matter. So imagine that the copy operation required a load from some region of memory. You know, these are simple scalars. What if they're an array? Right. If it's C++, I'm going to call the copy constructor. So there can be a lot going on with that copy the private variable from the original. So not to mention it's multiple threads reading from a single value, so there might be some caching effects. So there could be, on some environments, noticeable overhead. And when you're trying to take advantage of hundreds and thousands, I mean, we're writing little toy programs, and you know, I get 4 threads, 8 threads. Seriously, imagine if you start going 1,000 threads, 10,000 threads, 100,000 threads. Then those little itty tiny bitty overheads kill you. So yeah, you really don't want to use first private when you don't need to, but you need to use it when you must. Question in the back, yes?
So calling it private B, capital B, rather than some other name for the variable, you know, would be any benefit to that other than calling it the same name?
Well, if you had private, so these clauses only take variables that exist already and map them into a new region.
I'm saying, why would you do that rather than define a new local?
Oh, so what he's asking is why, think about private B. What's the benefit to doing it as a clause as opposed to just declaring B inside the loop or inside the construct? That is an actually excellent question. And there are different disciplines you can adopt as you approach multi-threaded programming with OpenMP. And many of us old-timers, one of our disciplines is we don't use private B. We always declare. And the reason is we want a program that has rigidly identical semantics if it's interpreted single-thread or multi-thread. When I put it in a clause, I'm now potentially changing its behavior relative to whether I run it with OpenMP or not. So there is a discipline that says that you avoid these data clauses at all costs because I want to write code that rigorously is the same with OpenMP or not. However, there's another discipline that says every time I add a line of code, I create another opportunity for a bug. Therefore, if I can do everything on my directives, I'm changing executable code less. So the other discipline says I will absolutely do as much as I can with those clauses. Both are right. The big thing is that when you develop your own discipline towards multi-threaded programming, you come up with your own rules that work for you. But you actually, your question lays a broader issue about what is the discipline, the design rules, the style guide you will apply as you write OpenMP. And it's not a right or a wrong. OK, I need to move on. Here's an exercise. This is a fun exercise. This is a program that computes the area of a Mandelbrot set. Right? I know what the answer should be, and it will actually print out what the right answer should be. But oh my goodness, I was sloppy, I was bad, and I wrote a buggy program. And I'm going to ask you to debug it. Now, I just have to say, how many of you know Mark Bohl at EPCC? Edinburgh Parallel Programming Center. Good, OK. Mark may see this video. Hi, Mark. Mark gave me this exercise. If you hate this this exercise and you want to swear at someone, okay, Mark Bull of EPCC is the one to swear at, not Tim Mattson of Intel. All right. So you can either take that as me deflecting blame, or for those of you who love this exercise, I'm acknowledging the brilliance of the contribution of Mark. But I am not devious enough to have thought this exercise up. All right? So you need to fix the errors in this program. All right? So, and there's a big hint. Gee, what have we just been talking about, folks? The data environment. I wonder if those errors have something to do with the data environment. Maybe they do. So at any rate, fix the program. It's called mandel.c, and you need to debug it. And this program is very nice in that it'll tell you what the right answer is supposed to be, so you'll know when you get the right answer. If you get the right answer quickly, there's multiple ways to solve this. So if you're one of the people who have experience in OpenMP and you go quickly through this exercise, then what your exercise become is implement it multiple ways and see if you can speed it up. Because there are other ways to solve this. All right, go for it. Go forth and fix. Here's my solution to the problem. All right? Big problem number one. Oh, and I'm sorry, right here I just have my solution. I don't have the original code. Here's the original code. And what you immediately realize when you get inside this loop is that test point has the global scope value it sees, but there's also this private copy. So it's the problem I told you about on that specific slide. The compiler, once you get inside test point, has no way of knowing which value of C you needed to do. So one of the first things you need to do is pass into test point through its argument list. So instead of a void here, I need to put the value. Yes?
So he was running this on some machinery that we have back at our work. And he didn't have to do that, and it was working out correctly. Because I was trying it locally on my laptop, and it was not working. So why would we get those differences?
It shouldn't work anywhere. I don't know what his machine was. I'm surprised it worked anywhere, because most OpenMP implementations I'm aware of, that would not work.
So it's not void anymore.
That would not work on a KNL. There had to be something else going on.
He was getting the right answer.
He might have gotten lucky and got the right answer. That's possible. And maybe it's possible some clever KNL compiler engineer figured out a way to disambiguate that and do it on behalf of the programmer. Nothing prevents them from doing that. But I would be really surprised, because I'm pretty sure the Intel compiler, I use the Intel compiler all the time. And even though I'm using it on my laptop and not a KNL, it's still the same compiler. So that was surprising. So the big one in this exercise is recognizing that you have to pass C into test point. Now the other thing to recognize is that I'm incrementing num outside. And that is a shared variable. That is a global variable. So I had to protect that with a critical section. One that gets a lot of people is this J. Several of you, as I walked around looking at your codes, I saw this one. Okay? Remember, the Pragma OMP4 will privatize the loop index of the parallel loop for you, but not any loops nested within there. So you have to make J private. All right? You had a question, yes?
We add collapse directed to the do we need to put J?
Right. So let me expand on his question, and I'm only going to do it briefly. Okay? beyond the Common Core, so I don't normally cover this as part of the Common Core, but it's applicable here. If you folks look at this, I have a for loop nested tightly within another for loop. They're perfectly nested, meaning there's no statements in between the two of them. And inside, this code is independent over both loops. There is a construct in OpenMP called collapse, which says take two or more perfectly nested loops, collapse them into one bigger loop, and then parallelize that big loop. So it would be pragma OMP parallel 4 collapse 2, because there's two loops. Okay? Then it would correctly privatize both the I and the j. And you would not have to, I do not believe, I could be wrong, but I do not believe you would need to explicitly privatize the j. I could be wrong. I know with me personally, I would rather over-specify than under-specify. But I believe the collapse would get you around that. I'm going to test that, though, later on. But collapse, where collapse becomes important, is what if endpoints is a small number, 100? You want a lot of loop iterations to give flexibility to schedule and keep all the threads busy. So there are times for performance reasons, being able to combine the loops is really important. So that's why we added the collapse clause. OK, there was a question back there first. Yes?
So why is EPS first private? I mean, there's no fundamental difference between first private and shared, right?
Right. OK. The other bug is, of course, EPS in the original code was listed as just private, which meant it had an uninitialized value. That, sir, was your error when I looked and saw an error and said, oh, I see another error, then walked away. Okay? And he's staring at his screen because he didn't hear this. So that's OK. Yeah. So EPS, if it's private, that's uninitialized, and who knows what you're adding if you do that. OK? So his question was, my solution here is to make it first private. What that means is each thread has its own copy to look at. Remember, I don't trust compilers to be smart. If I left it shared, I have a correct program, but now in principle, I have every single thread reading the same address in memory. Now, any compiler worth calling itself a compiler will take a read-only variable like this and park it in a register and leave it there. So any reasonable compiler, it should not matter if it's first private or shared. Performance should be exactly the same. But a particularly stupid compiler, it might matter. So I call it first private, but another solution is to make it shared. That is a correct solution as well, because it's read-only.
First case you're talking about where the compiler is not, what can it do?
Well, OK, let me be clear, folks. If I had a situation, for example, if it was a pointer, so a compiler, if I was walking a pointer data structure, so now the compiler cannot safely make assumptions on that data. What that means is each and every thread is going to issue a read of that address. What that's going to mean is the cache coherency protocol is going to say, load this cache line. So now I'm going to potentially have a load and a load and a load and do a whole bunch of loads. Whereas if I make it private, I now have got a location on my thread stack, and I might be able to decrease those loads to memory. But we're getting into some pretty low-level details, and it's going to vary compiler to compiler. But overall, it's a correct solution calling this private. It's a correct solution calling it first private. And I'd have to look at the assembly code and optimization level. There's a lot of glitches on. Yes?
So one thing I tried to do unsuccessfully was do reduction on num outside.
So another solution to this, and actually potentially a better solution, is to use a reduction on num outside, but then I have to pass num outside as an argument to test point, because I don't want to mask the global with my private copy. So that I would then pass num outside in as argument to this function, and I would not have it as a global variable.
And do you need to tell it inside of the sub-function test point? Do I need to tell it anything like reduction again?
No. Remember, Reduction is far more subtle than people give it credit for. So let me repeat this again. When I have a reduction of a variable, a reduction clause, it's going to create a copy of that variable just as if I used private. Okay? Nothing special, nothing magic, doesn't care. Compiler doesn't even know it's a reduction, doesn't care. So that creates a private copy of that variable with the same name. It will then do an initialization given the identity of the operator, which for addition would be 0. At that point, it's just a private variable with an initialized value. That's all it is, nothing else. I can use any operator on it. I can pass it in a function. I can do anything whatsoever I want. Then when I get to the end of the construct, now it will go and say, oh, that's a reduction variable. It will then use that operator to safely combine all the local copies. Then it will combine that combined value with the original variable, and you're done. So inside, it's like, no, this is just another variable. I can do anything with it. I can do whatever I want. Think about memory in a computer. It's an address-based system. You define addresses, and I'm going to do loads and stores into those addresses. A variable is nothing more than a name for a convenience of the human to keep track of these addresses. So consider a single variable called A. This variable can exist in memory. You know, I've allocated it, so it's got an address in the DRAM in memory. But it also can sit in a cache. So I can have two different copies of that variable. It's, of course, while this slide doesn't show it, it's even worse than that, because I could have another copy of that variable sitting in another cache. It's even worse than that, because I can have another copy of the variable sitting in the register file of one of these processors. I can have dozens of copies of that variable with different values spread throughout the system. And in a modern CPU with all those caches, that is normal. This is not a rare event. It's actually a typical event. A memory model is the set of rules that determines for any given load which value of A will you see. That's what, when a computer scientist is being correct and they talk about a memory model, that is what they mean. Because there can be multiple values of A spread all around the system in L1 cache, L3 cache, DRAM, register file. They can be all over the place. And there has to be an unambiguous what value you see when you issue a load, you know, when I go to read that value. So the memory model gives you the rules that define what value you'll see. This is also referred to as a memory consistency model, because that is the issue. You want to have an inconsistent value of A. Now, if I do not have a data race, every system with a reasonable memory model will give you a consistent value. If I have a data race, then it doesn't have a clue what value to give you. Remember, a data race is when you have unordered loads and stores mixed. So you have multiple people reading from a location, multiple people writing to a location, and those are not ordered. Then it's like you're asking for it. You get what you deserve, and you deserve to be hit in the face, because that's evil. All right, so that's what the memory model is. Now, I'm going to hopefully not bore you too much with a little anecdote. All right? I'm a theoretical chemist. I'm really a molecular physicist. Because most people, when they say they're theoretical chemist, it means they do electronic structure calculations. I find those things utterly boring. Okay? I did quantum scattering. You know, let's smash things off each other and do quantum mechanics tracking all the energies and all the particles, all the energy flow and all the particles. So cool stuff. At one point in my career, it fell on my shoulders to actually write the memory model for OpenCL. So the memory model in OpenCL right now, I led the small team. I basically wrote it. Okay? That seemed like a reasonable thing because we decided we're going to base it on the C++ memory model. And the C++ memory model already existed. Well, not quite. You see, the Java memory model was created a long time ago, and the group got together and created it. This is like 10 years ago. And the memory model they created crashed and burned. They released it, they published it, it just fell apart. Did not work. OK, same smart people got together, and they rewrote the memory model in Java. All right? And they kind of got it right. It still had serious flaws, but they kind of got it right. Then C++11 comes along, and they say, you know, guys, we're going to put threads right in the heart and soul of C++. We need a memory model. So that same team came together and said, third time's the charm. We're going to get it right this time. And they wrote the memory model for C++. Now, the OpenCL people, that was me, the ANSI C people, other people doing languages research, all said, OK, great. We will adopt the C++ memory model because the people working on it have spent their careers working on memory models. And this is their third try at getting it right, and we trust them to get it right this time. So they came out with it. And if you are a glutton for punishment, if you're like some weird sadomasochist, bizarre type person, you know, I challenge you to download the ANSI C++ specification and study the memory model. Okay? It's really, you have to be a weird, twisted human being like me to do that. But I did it, and I worked with a team of really smart people. We wrote the OpenCL memory model. OK, we're like 3 months away, maybe 2 months away from releasing OpenCL 2.0 with its new formal memory model. We were excited. And the C++ memory model had been out a year at this point. So of course, it had to be right. And we get this frantic phone call from our friends on the ANSI C++ committee. Oh my God, oh my God, oh my God, no, our memory model's broken. You got to drop the following statements from your memory model because we don't know what to do and it's just broken. Now, the reason I mention this is the people involved with these memory models are really, really smart. They are vastly smarter than me, and I'm not being sarcastic or snarky when I say that. These are very smart people that work on these memory models. And they couldn't get it right. After 3 tries, they couldn't get it right. All right? They still have flaws. So I say all this, and by the way, we went through and did the patch. It was that out of thin air problem. I don't know if you've ever heard of the out of thin air problem. But it's if you take and initialize a variable to 1, and you have some ensemble of threads, and they're all writing 0 to that value, and then you do a load and you get 42. It's like that value 42 appears out of thin air. And the point is there's a combination of, remember, this is all a complex, convoluted rule-based system. And there's a combination of weird corner cases where that is possible. It's called the out of thin air problem. And that's when I say there was a flaw in their memory model, that's what it was. Now, the reason I mention all this is I want to leave you with the impression, I'm going to say a little bit more about the memory model, but I want to leave you with the impression that if you ever try to write code, the behavior of which depends on the low-level details of a memory model, I have some advice for you. Don't. Just don't do it. Now, if you come back and say, no, I really do have to do this, then I'm serious. Don't do it. But if you really must, then what you do is you include in whatever your grant funding proposal is a large quantity of premier beer or wine. You find a graduate student or postdoc who lives and breathes memory models. You will find them. These people exist. And you copiously bribe them with this high-quality beer or wine, whatever their poison is, and you get them to do it for you. This is the epitome of code even an expert should write. And let me tell you how serious I am about that. If I had to write a lock-free data structure, see, this is the sort of stuff where you start having to deal with the low-level details of a memory model. I teach courses in writing lock-free data structures. I know how to do it. I'm an expert. I would never write a piece of code with lock-free data structures that my life depended on. I would never even think of doing it. So it is really hard to get right. So I'm going to show you in OpenMP a flavor of the memory model and what we do to protect you from it, and the level you can safely work with it. And if you want to go beyond that, that's fine, but I don't want to be anywhere nearby because I have a hard time hearing screams of anguish from disappointed programmers. So what OpenMP has is called a relaxed consistency model. And this, by the way, is what pretty much all multi-threaded systems I'm aware of have. Because if you have strong consistency, you basically can't get performance. Relaxed consistency means you recognize that threads have a temporary view of memory. Remember when I showed you back here that, processor 3 sees a value of A in its cache. So it has a temporary copy of A sitting in its cache. That may not be the same as the value that's the permanent copy in DRAM. So threads have a temporary view of shared memory, and at any given point, it may be inconsistent with the view seen by other threads. So even though it's one copy, a relaxed consistency model says we allow the threads to do a read of A and to see different values at a given point. So there are specific points in your program where you need to force them to be consistent. We have a construct in OpenMP called flush. And flush does that. OK? So let me describe a flush operation. And it's really hard not to get all jargony here. A flush defines a sequence point in C or C++ jargon, Fortran jargon as well. You talk about the sequence points as you move through program text. And you can think of it, the granularity of being statement by statement by statement. It gets subtle because there's sometimes multiple sequence points in a single statement. But it's a fixed chunk of processing as the compiler goes through as it's interpreting a set of statements in a program. So a flush defines a sequence point where it says this thread will do what it needs to see and present a consistent view of memory. So what that says is the thread says all loads and stores before this sequence point will complete and be committed to memory. This thread says none of the loads and stores that overlap with this flush set will begin until after this. This means the thread's going to have to take any values in its cache, any values in its register file, and write them down into memory. Okay? Now, a flush is not a synchronization point. Because remember, synchronization defines an order constraint between threads. This does nothing about an order constraint. All it says is a thread calls a flush, and it says, I will make my view of memory available to other threads, and I will go out and look at the value of these variables that are in memory right now. That is all the flush says. It doesn't say anything at all about what other threads do. That's important to note. All right? So just as a little piece of jargon, some shared memory environments use the word fence instead of a flush. But that's what a flush is. Now, here's what we do in OpenMP. I want you to be aware of flush. I want you to know that concept. I want you to be aware of the concept of relaxed consistency and the fact that threads can have different views of memory. I want you to know that. I want you to never call a flush. They're in OpenMP, and in the notes, you'll notice in the section beyond the Common Core, synchronization more than you ever wanted to know, I talk about using flushes there. So if any of you are particularly weird and twisted tonight after dinner, you can look at that and talk to me about it, okay? But it's there. But what we do in OpenMP is we predict where you need memory to be made consistent. And we imply a flush for you. So you are calling flush all the time, you just don't know it. And that's the way it should be. Okay? So if you want to write code where you need to call flushes, Learn about them and go for it. You're digging your own grave. Okay. We have very carefully figured out where you need flushes. So we do a flush on entry and exit of a parallel region. So when you enter a parallel region and create those threads, first thing those threads are going to do is make sure they have a consistent view of memory. When threads complete their execution, before they do the join, they're going to make a consistent view of memory. All right? Likewise, anywhere you put a barrier, okay, before they exit that barrier, they're all going to do a flush. So anywhere you put a barrier, that's fine. A critical region, if you think about it, this is where it's essential. Because a critical region I may have multiple threads, reading and updating shared values. There it's very important I do a flush on entry to the critical region, so that whatever I'm doing in the critical region, I know I've updated to the consistent view. And on exit to the critical region, I'll do another flush. Likewise, for the other synchronization constructs, we imply the flushes. So basically, we try to anticipate where a flush makes sense, and we do it for you. I just want you to have in the back of your head that this thing called a flush exists, and that some people write code that needs to explicitly manage flushes, that OpenMP handles all of that, and you probably don't want to go there. That's definitely a case of you need an expert trained in the details of concurrency theory to do that. And the sort of people in this room, most of you, should never go there. And I shouldn't be quite so silly. There might be 2 or 3 of you in a room this size who needs to go to that level of doing that. It's not impossible. There are people that need to go there. But if you're a physicist or a chemist or an engineer who's doing computational sciences, so you're writing PDE solvers, those sorts of people probably should never have to deal with this. If you're writing a general arbitrary framework with distributed data structures that need to handle very, very efficiently, lots of threads going inside and updating things, you probably do need to learn all of this. So it really depends on where you come in that compute stack. So maybe some of you people with the computer science symbol on your card, you might have to go there. But yeah, I don't know. It's funny looking, you're kind of shaking your head. You might have to go there. So we'll see. All right, so that's enough. That's mostly just warning you that this whole dark thing exists, and it's there, and hopefully you never have to go there. So what we have now covered has been in OpenMP pretty much since OpenMP 1.0. Few little changes that came between 1.0 and 2.0, but this is like old, original core OpenMP. So now we're going to talk about something that came into existence in OpenMP 3.0, 2005-ish. And Jack Donguera referred to this morning with tasking, so that's where we're going. And it handles a whole class of programming that we couldn't handle before, which is called irregular parallelism. Now, I'm going to use this term very loosely. It just does not have a precise definition I'm happy with. So look, I'm just going to say, if you're writing code where you have sparse data structures that you're dancing all over, or you're writing code where the control structures are not basic for loops, they're not predictable control structures where you can determine the iteration space at compile time, right? If that's the case, I'm going to call that irregular parallelism. And the quintessential starting point in irregular parallelism is traversing a linked list. So all I'm going to do is I'm going to have the pointer to a list. I'm going to traverse that list and do a processing on the pointer for each point in that list. And then I'm going to increment to the next point. So it's a linked list. Notice there is no pragma OMP parallel while. Okay. The reason is if you think about OpenMP, you're having a directive and you're telling compiler, transform this code so it'll do the right thing. Well, it can do that if it can have a closed form expression for the iteration space. That's what it can do for a for loop. It can't do that for this. It doesn't know what to do. All right, so what is your next assignment? And you're only going to get 15 minutes on this. All right, using OpenMP, traverse a list in parallel. Okay? And for those of you who like to cheat, the specific exercise, you are not allowed to use tasks. You are rigidly only allowed to use these constructs. Do not cheat. Do you got that? Okay. There's my ringer over there, right? Yeah. The point of this, now, I have in your folder linked.c. Let me warn you. When you look at that code, you're going to go, oh my God, there's all this code. Defining the linked list, initializing the linked list. We do a stupid computation inside the linked list. Ignore all of that. All you need to look at, in fact, let me just show it, because you can waste an awful lot of time reading the code. And the best thing to do is just don't even read it. Okay? I took VI and I said, go to the last line of the file, because I'm skipping all that other crap. You just want to look at this while loop, all right, and figure out, this while loop, traverse the list. Okay, that second traversal is just releasing the memory. Don't even try to do that. It's just this one traverse the list loop, all right? You want to traverse that in parallel. You want to create multiple threads to go through that so that that process P step happens by multiple threads. And what you'll find, this is pretty far down. Yeah, this is down at 91. The first 75 statements of this file is creating the linked list data structure, defining what process work is, and just take all that as a black box. I just want you to say, here's this while loop. To traverse a linked list, I want to write a multi-threaded program that does that. You have 15 minutes. Go for it. Okay, let's continue. Remember, my main purpose of this exercise was twofold. One, to give you something we call in the coaching world random practice. So block practice is most of what we've done. I say, let me tell you about the parallel construct. Here's an exercise, use the parallel construct. All right? That's called block practice. I tell you what to do, and you go off and do it. The Mandelbrot exercise and this exercise are random practice. I give you a problem, and I say, solve it. And you don't have a clue which of all the constructs we've talked about you have to use. That's called random practice. Block practice is the best way to get people to nail down inconsistencies in their initial understanding. Random practice is the best way to move something into long-term memory. So in an ideal pedagogy, you do you present small concept, block practice, small concept, block practice, big random exercise for random practice. So this was a random exercise, a random practice exercise for you to have to pull across all the different parts. So some of you who came into here with OpenMP experience might have gotten this done. Others of you in the time allotted probably just got frustrated or learned something looking and thinking about how to solve it. It could probably take you another 10 or 15 minutes to solve it. This one was not easy. In fact, this will be a good one when we come back tonight after dinner for you to play with some more if you wish. This is a good evening program. But I'm going to show you my solution. All right, here I go. Step number one. I walked the entire list to figure out how many elements there are, because I don't necessarily know in principle. Turns out, looking at the code, you did know this. But as I said, in a general solution, you shouldn't assume that. When someone hands you a pointer to a list, you don't know how long it is. All right? So now I know how long it is. Okay? Then I don't show it, but I allocate an array of type node of that size. All right? Now what I do is I walk the list a second time This time, I save the pointer to each location, each node. So I walk the list and save that address. Right? And I know how many items there are because I first walked the list to get the count. Now I can do a simple loop, parallel loop. And in this case, I got different results if I used a static schedule versus a dynamic, I think. Well, yeah. I used the default schedule versus static. But let's not go there. So, yes?
What happens if your process work changes the nodes in the linked list?
Yeah.
Then you're in trouble, and this approach doesn't work.
What would you do?
I don't know. I'd have to think hard about it. Yeah, that would. I'm not sure if there's anything could do about that case. That would be really tough. Really tough. But I don't know. OK. So a few things here. I had to make 3 passes through the data structure to do that. That's a lot. Remember, if you've heard anything in the last few days, it's compute is free, memory movement's everything. All right, I just moved through memory 3 whole passes through my list data structure in order to come up with this solution. That just sucks. But not only that, what started as this simple little elegant while loop turned into 1 while loop and 2 for loops. I mean, it was ugly, the amount of code I had to create to do this. So surely, there's got to be a better way to do this. This can't be the right way to do this. Well, there is a better way, of course. And now I'm going to tell you. Tasks. Tasks were added to OpenMP largely for handling exactly the sort of examples I just showed you. So a task is an independent unit of code, independent unit of work, and it consists of the code to execute, but you also have to define the environment that you're going to associate with that task. So here's a cartoon version. I always like pictures because there's some people who need to see pictures to understand things. So imagine I have 3 tasks, the pink task, the green task, the blue task. And in a serial program, they go one after the other. And what I'm going to do with tasks is I dump them into some kind of task queue structure. And then I say, threads, go at it. And they will then work through that task queue structure. And so they can go ahead and balance the load between the tasks and execute the code. So that's how the tasks work. Now, so when you define a task, the code, not surprisingly, is a structured block of code. So we're going to use a structured block. And when a thread inside a parallel region encounters a task construct, I'll show you that soon, it's going to package up the task. It's going to package up the code. According to some rules I'm going to give you, it'll create the data environment. And then it'll either execute that task right away or will defer it. So this is the jargon we use in OpenMP. A task can be immediately executed, or a task can be deferred for execution. And defer just means I put it on a queue to be executed later. All right? And tasks can be nested. All right, so I don't like it, but from day one, the people working with me on OpenMP hated nested parallelism. I loved it. I find operating systems handle lots and lots of threads really, really well if you trust them. And so we could be able to build runtimes that let us nest threads, and basically threads become the task. That was always what I wanted. I was overruled, probably for a good reason. I mean, one of the fun things about working on a language standard like OpenMP is you get to work very, very closely with very, very smart people coming from different areas than you do. I have to spend a lot of time with compiler people and operating system people who I never want to talk to. I mean, no one wants to talk to those people. But I learned a huge amount. And that's what life's all about, is learning. So at any rate, they would submit that the right way to do nested parallelism is tasks. And right or wrong, that's what we do in OpenMP. So Most of the times you might think you want to nest parallelism. Probably what you really want to do is nest tasks. So tasks can create tasks, but now instead of creating these objects that the operating system has to swap in and out of an execution context, you're now just filling up these queues of work that have been deferred for execution that can later be executed. Now, before I go further and actually show you your first task, I know the anticipation is building. You're all like on the edge of your seats going, oh my God, show me this amazing task construct. But first, here's another work share construct. This is one we use a lot with tasks. It's called single. And believe it or not, this is a work share construct. What it defines is a block of code, and only one thread will execute that code. Now, since it's a work share construct, what do you think is going to happen right here? Barrier! I don't know who said it, but yes. All work share constructs imply a barrier. So here I create a team of threads. And you know, this is what we used to have to do with MPI all the time. And some old-fashioned people like me still do it. In MPI, the original libraries were not guaranteed to be thread safe. So when you were mixing OpenMP and MPI, you could get some really weird behavior if you weren't careful how you did that. So one of the ways to deal with it is you made sure that only one thread ever called MPI. So I would have all my stuff done locally, and then one thread would exchange the boundaries, and inside that function exchange boundaries is where all my MPI is. But I know that only one thread ever calls it, so I don't have to worry about if the MPI libraries are thread safe or not. And then after that's done, because there's a barrier at the end of the single, I go on and do other things. So one thread does the work, and you don't know which thread. It's any one of the team of threads. In a good implementation, it should be the first thread to hit it. Drops into the single. And then all the other threads in the team will wait at this barrier. All right? And yes, indeed, you can put a no wait there, because it's a work share construct. So if you want the other threads to not go on, just put a no wait. Now, I can show you how the task is used. Typical usage model. I have a team of threads that I'm going to create, pragma OMP parallel. And then one thread's going to fill up the task queue data structure, while the other threads sit at a barrier and do the work. So here I have pragma OMP parallel, so I'm creating a team of threads. And then I immediately have a pragma OMP single. And now I'm going to have whichever thread hits that is now going to create tasks. And that is pragma OMP task Fred, pragma OMP task Daisy, pragma OMP task Billy. 3 different tasks. These could be brackets for structured blocks. Remember, this is just a structured block. So I could have the angle brackets and have a bunch of code, or it's just a single function. So I've created 3 tasks, and all the other threads are going to sit here at this barrier. OK? And they won't go past that barrier till all the tasks are done. So create some threads. One thread packages up the tasks. I create 3 tasks. And they're going to be executed by some set of threads as they get to them. And remember, the beauty of it is this is automatically load balancing. It's sitting in a queue data structure. Threads will grab a task, do the work. When they're done, they'll go get another one. So if the tasks are really, really different in the length, this is really elegant. Yes?
Yeah, I assume that this is non-blocking, so that single thread will assign that task and then assign the next one, and it's not waiting for that to complete.
Correct. So let's be really clear, though, because it's much more subtle than that. Okay. So the question was, because the camera doesn't pick up the question, you know, is it non-blocking? So that it doesn't wait for a task to complete before it goes to the next. OpenMP doesn't define that. You have to have, with a tasking system, you have to have complete flexibility on how that occurs. For this particular case with 3 tasks, it may not seem like a big deal. So it's going to hit the task construct, and the thread will either immediately execute the task or defer it. A correct implementation of OpenMP would serialize this. One thread calls this. Oh, that same thread calls this function. Oh, that same thread calls this function. That is a legal OpenMP program. So the thread, the jargon we use is the thread encountering the task construct may either execute the task or defer it. Now, you may be sitting there going, why would you leave that vague? Why wouldn't you just say it will defer it? Because doesn't it seem nuts that a correct program could serialize that? All right. Imagine this was a loop inside here. Imagine the loop had 1 billion iterations. Imagine in the bottom of the loop was a task construct. So now I'm telling that single thread, create 1 billion tasks. Now a task is going to create the data environment, the function pointer, all right? There's some memory associated with that. So if I just all of a sudden create 1 billion tasks, I'm probably going to overflow whatever data structures I've set up for keeping track of the tasks. So we have defined OpenMP very, very carefully so that the runtime system can look at the task queues and go, there's no more room for other tasks. So you know this thread and the single that's going through and creating tasks, you know what? I want you to work on tasks for a while. So it can stop creating tasks and start computing tasks. And so the definition of how it responds to that task construct gives it that flexibility. So that's why it could do something really stupid. But you know, for 3 tasks, it's going to put them on the queue, and then the other threads are going to execute them. But it's built in there so that we expect an implementation to be intelligent enough to know when you should stop creating tasks and just computing on them. All right. Yes?
So here's my assumption. So in a NUMA system, one of the thread creates all the tasks, and all the tasks is in its queue, while other threads have to pick up work from that thread's task.
So
does that happen?
Let me be clear. The language definition doesn't define what happens. I don't know what happens because I've personally not spent a lot of time working on those systems. You think I would coming from Intel, but I haven't. But you hit upon a serious problem with tasking systems. And it comes down to what are the data structures you use for managing all of those tasks. Now let me just say that I'm not sure of the details of what Intel does with this, but our tasking technology is phenomenal. It's based on thread building blocks, which dates back to 2000-ish by Arch Robison. And Arch, if you're watching this, hello Arch. Sincerely, Arch is smarter than everybody in this room. Really, the guy is very, very smart. And he built really high-quality tasking software. And basically, we studied what Arch did, who worked for Intel at the time. We studied what he did, and it influenced everything we've done since then and how we build our tasking systems. So, I mean, this is why someone like Jack Donguera, who's also a very smart guy, his team was thrilled when they could give up their tasking environment and just use OpenMPs. Because this is not the sort of software, if you're a mathematician or a physicist or most of the other types of people in this room, this is a full-time job to write a good tasking system because of exactly the issues you're talking about. So that's, how do you build distributed tasking queues? And in a NUMA environment, that could be very important. So I don't know exactly what we do, but in building tasking systems, that is exactly the sort of mindset you have to think through. It can get very sticky. Yes?
If I added a no wait clause behind the single and then there was additional work after the single clause, would those threads that don't work on the single environment first work on the stuff that comes afterwards, or do they work on the tasks like somewhere in between? Like is there priority between task and other work?
So yes, if I had a no wait, then when we get to the end here, the other threads are going to keep going. And they're going to go right on and do whatever work follows this bracket until they hit this barrier. And then they won't go beyond that barrier until all the tasks are done.
Okay. And they would only, okay.
So they would do whatever work I wrote here. In other words, the single construct is not aware that you're creating tasks inside of it. It doesn't care. So you can reason about the behavior of the single construct in isolation. And all the single construct says is one thread does the work, the other thread's wait at a barrier. Period. And the no wait says one thread does the work, don't put that barrier.
And is it the threads that are waiting that are picking up the work, or is it new threads that are created for the task?
Let me be abundantly clear. And you know, I want to just emphasize, I love all these questions because this is getting the deep, deep understanding of OpenMP, which is what I want. The question was, are new threads created to do the tasks, or is it the threads that are already there or that are sitting at a barrier anyway doing the work? It's that second one. Look, to a first order of approximation, there's some stuff we've added with the GPU world and the device world. Let's ignore that for now. The only way to create threads in OpenMP is with a parallel region. So you do not create new threads to do the tasks. That's why I have to create the team of threads that are going to do the work with the Pragma OMP parallel, create the tasks, and often I do it with a single, but I don't have to, by the way. I can create the tasks in parallel. Okay? It's just this is the normal pattern. It's just I reason about the program by having one thread go through all the code that creates the tasks, and then the other threads do the computing. But there is nothing that says you have to do that single. I want to be really clear. But the common pattern is you create the team of threads, one thread creates the tasks, everyone else waits, and it executes the tasks. Now, I want to stop because I have an exercise for you. And this is a short and quick exercise. Write a program. The program is going to print one of two strings. I think race cars are fun, or I think car races are fun. All right? And you're going to use tasks to build a race condition into your program. All right? Remember, race condition is a program that gives you different behavior depending on how threads are scheduled. So we're purposely writing a race condition. But as long as you don't have a data race, it's still a legal program. This is why I like to distinguish between race condition and data race. Now I'm going to tell you, I'm sorry, I'll fix it for next year so I have the starting point. Write a program that has a printf that prints I think, and then have it print at the end are fun. And then create tasks. One task prints race, the other task prints car. Right? And I'm sorry, I misspoke. You want one thread that prints, one thread prints this, the other thread prints, right? I'm sorry, start over. Start over. So you're going to have a printf that does SR fun. You're going to have another thread that, at the beginning of the program, before a parallel region, have a printf, I think, space. After your parallel region, you'll have a print SR fun. Inside your parallel region, you want two threads, and you're going to have two tasks that print race and print car. Do you see how that's going to work? And what you want is a data race. So when you run it, sometimes it prints race cars are fun, sometimes it prints car races are fun. Does that make sense? And I apologize, that's more just pure C hacking than I meant. So this is quintessential block practice. I'm just trying to see, did you really understand what I said about tasks? At any rate, that's okay. This was the quintessential block practice exercise. And what I confirmed with this is that you understand this basic pattern of you define a single, that thread's going to create the tasks, the other threads are going to wait and execute it. Okay? And I didn't get the race, but that's up to how things are scheduled. Excellent suggestions on the three threads, because
it worked for me. It's good.
That's good.
But it doesn't work for me.
It's weird.
And I'm running at 300.
Okay. Well, we have to get going because we're down to our last 20 minutes. All right, let's talk about data scoping with tasks. They're pretty much the same. There's a couple little differences. So the issue is that when you package up a task and defer it, what value does it see? Because think about it in time. You're packaging it up, and it could be quite a while after you created the task. And who knows what changes have been made to those variables before it executes. So, you know, if it's shared on the original variable, it's going to be shared inside. Okay? If it's private, then you're going to create the reference inside to uninitialize. That's just the same. The important one to remember is first private, because that's very important. In fact, this is one used a great deal with tasks. First private will create a private variable, and it will initialize it from the original variable at the time the task construct was encountered. Okay, that is really key. Because think about it, for example, if you're walking through some data structure in a linked list, and I call a task and I have a first private on that, now the next while statement is going to increment that pointer. Okay? So I have to know that when I define the task, it's going to create the private for whatever variable I'm creating, and it will initialize it to the value at the time the task construct was encountered. That's the only logical way that you can reason about in a program. So it's pretty straightforward, I think. I have a parallel region with a shared A and a shared B. I create a task, and now I'm inside. And A is shared because it was shared on the encountering context. C is private because it occurred inside. Now look at B. B was private on the parallel region that encountered the task. This is another example of us trying to think about the way these constructs are used and make the default behavior the safe behavior. And we figure almost any time you're using tasks, and I'm talking about the issue with B, almost any time you're using tasks, if the original variable at the time you encounter the task is private, chances are you wanted it to be first private. Okay? You want the task to be created, and the data environment you created, it's going to have its own copy of B with the task capturing the copy of the original variable. So if a variable is private in the region when you encounter the task, it's basically going to capture the value of that variable and package it up with the task. Now, way, way back, long, long ago, when we were creating tasks in OpenMP, they wanted to create a new keyword, capture. And I'm the one who argued, darn it, no. We want to have as few keywords as possible. And you think about the semantics of a capture, it's identical to first private. Right? Capture means create a copy with this name and initialize its value. Well, that's what first private does. So pragma OMP task first private B captures that value of B for when you create the task. And we assume by default, if when the system encounters pragma OMP task, if it sees something that's shared like A, oh, that's shared, no problem. If it sees something that's private, oh, you meant first private. It'll do that for you. Okay? So now, let's do it. Go back to that linked list, and using what you now know about tasks, parallelize it. Go for it, it'll be fun. How many people are tired and just want to stop doing exercises till after dinner? Really? Okay, give this a try. If you really understand everything we've said, and now you know that linked code very well, Hopefully you kept the original around and didn't. So, but starting from that original, you should be able to do this really fast. As you can see, with tasks, this is an elegant and simple solution. I create the parallel region. I want one thread to do the while loop. Then inside, I'm going to do pragma OMP task. And because I like being very, very explicit, I have a first private P on the process. Done. It's really that easy. So tasks are huge in OpenMP. And a lot of the developments in OpenMP have been to refine and expand and deepen this model. So I make a copy of P, and I get this beautiful thing going here. Okay? So when tasks complete, we've already talked about, when basic threads waiting at a barrier will complete when we'll wait there and do the work on the barriers. When you get to the barrier at the end of a parallel region, this is important. When you get to the barrier at the end of a parallel region, none of the threads will exit until all of the tasks in the parallel region are done. And I mean all of the tasks. Now there's another construct called task wait. And it says wait to the tasks in the lexical extent of my code to complete. What do I mean? It's easiest with an example. It's easy. So here I have my case again. This is the first slide I showed you with tasks earlier. Where I'm going to create Fred, I'm going to create Daisy, I'm going to create Billy. All right? What task wait says is Fred and Daisy must complete before Billy starts. And I'm going to stick my neck out here, but I believe task wait implies a flush. You don't have to think about, well, are the results of Fred and Daisy visible to Billy? Yes. The results of Daisy and Fred are going to be visible to Billy because we've done the flushes. All right? Yes?
It seems that you could replace a lot of other things with OMP task. You could just do like tons of loops.
So yes.
Is there more overhead with this so that it's not?
I'm glad you mentioned that. So I want this on the camera, so I'm going to say this very clearly. Tasks are extremely powerful, and you could replace an awful lot of what we've talked about with OpenMP with tasks. You could just really go for it with tasks. Look, they add overhead. You're taking a block of work, you're creating a data environment, you're copying that into memory, you're putting onto some kind of queue data structure. The gentleman over there was talking about in a NUMA environment where, now you have these threads over here, they're going to have to go to that central queue data structure. Oh, that queue data structure, when I mentioned that concurrent data structures, how I will only let an expert write them, that queue data structure is a concurrent data structure. So it's got all sorts of synchronization built in so multiple threads can get to it. If you can do it with the other parts of OpenMP, you're almost always better off to do that. So tasks are for irregular problems, are for a directed acyclic graph where you have some kind of strange dependency pattern. We haven't talked about dependencies yet, but there are cases where you have to use a task, but only use them when you have to use a task. All right, so task wait defines a point where you can wait in your program, and it says that the tasks that occurred before the task wait will complete. But let's be clear. Notice I said within the lexical extent. What if Fred created tasks and Daisy created tasks? See, those are tasks being created outside the lexical extent, outside the code of this construct. That's what I mean by lexical extent. All right? Those will not wait. Task wait just says Daisy and Fred. But Daisy and Fred may complete and say, we're done, and leave behind tasks that we're executing that they created. Task wait doesn't care about those. The task at the barrier on the parallel, it will care about those. So if Fred and Daisy created a bunch of tasks, task weight doesn't care. It just weights Fred and Daisy. But this barrier here, it cares. Even the tasks buried deep inside Fred and Daisy and Billy, it'll wait for those to finish. Does that make sense? Okay. Believe it or not, you now know enough to do a huge amount about tasks. Now I'm going to explain this example, and then we'll be done. Let's look at this example in quite a bit of detail. So this is a perfectly horrible way to compute Fibonacci numbers. Let's just get that out of the way. Yes, I am well aware there are well-known, better algorithms than this one. But you know how that Pi program is the hello world of parallel programming? If there was a second candidate for it, for irregular case, this would be the hello world program. So I have a recursive algorithm. And what I'm going to do is I'm going to call it on my number. And what it's going to do is I have an exit case. So if n is less than 2, it's so easy to compute, just return. All right, so if n is less than 2, the Fibonacci number to return is 0 or 1. So easy. And then for the other case, I'm going to call it x equals fib of n minus 1, y equals fib of minus 2, return x plus y. That's just a direct expression of the recurrence relation for a Fibonacci number. It's directly mapped it in there. So it's a recursive definition. Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. That's all I have to do. Okay? Let me show you how I do this in parallel. I want you to think about it a few minutes, though. Think about how you would do this with tasks. I don't want to give this to you as an exercise, though, because it's a little tricky. All right. So the task creation is inside my Fibonacci program. So I'm going to create in main my team of threads. I have a single, so one thread is going to call Fibonacci. And all the other threads are waiting at that barrier. Now the action goes inside the recursive function. So now I'm going to go inside the Fibonacci. And remember, I'm just doing that recurrence relation that I showed you on the previous slides. F at n equals fn minus 1 plus fn minus 2. I'm just doing that recursion relation. So I have fib of n minus 1, fib of n minus 2. Each one's a task. And then I need to add them together. But this add together does not make any sense at all until those two return. So let's just make sure you're with me that far. Okay? I'm going to call the Fibonacci function on n minus 1. I'm going to call the Fibonacci function on n minus 2. I have to wait for them to finish because this sum of x plus y makes no sense if they're not done. So task wait. Okay? Now, here comes the other part. Private variables, whether they're first private, irregular private, what do we know about private variables when you go outside the block? Gone. They're gone. Therefore, x and y had better be shared, otherwise they don't exist for this sum. So x and y, I explicitly make them shared so that when those tasks return, those values at those addresses are visible for me to do the computation. Calling them shared there is important because without the shared, what would they be? It's a good exercise. I probably should have the sequences of slides. First private. Because x and y are declared inside the function. So as far as OpenMP is concerned, they're private to a thread. So if you leave it alone, when they hit there, they're going to be first private. That means x and y will not be available for that sum at the end. So I have to make them shared. There are wonderful ways to dig yourself in a hole with this stuff. There really are. Now, this is a phenomenally important pattern. Okay, SPMD is very, very important in a lot of grid-based codes. You know, I'm doing a rather regular mesh, a lot of mesh codes. I can very cleanly handle with SPMD. But there are other classes of codes that I handle with an algorithm called divide and conquer. Okay, and this is a very common pattern. In divide and conquer, it's basically the heart and soul of recursion. I have a way of splitting a problem into subproblems, and I do it recursively. So I keep splitting the problem into subproblems until the problem gets so small that instead of splitting, I do a direct solve. That gives me sub-solutions, which I merge to get the global solution. And in general, with this pattern, I can do computing at the split, I can do computing at the solve, or I could do computing at the merge. Now, I'm not going to have time to go there. If I did a second day of OpenMP, which if you think we should do one, you need to tell the organizer of this event to have Tim come back for a second day of OpenMP. Or a third day. I'll take over this event. Yeah, no. But, if I had the second day, we would spend a lot of time with these, because if you ever heard of cache-oblivious algorithms, this is the trick they use. The idea is that I split up my block of memory, and because the caching system keeps track of how I'm splitting up the memory, I can naturally, without having to do weird blocking, end up with subproblems that are operating out of data that's in a cache. So that's one instance where these are used. Also dynamic programming algorithms, a lot of bioinformatics codes, if I were going to parallelize them, use this type of algorithm. So a lot of symbolic reasoning codes. So when you start moving away from all the worlds of mesh, all the worlds of finite difference or finite element code, you start running into these. So they're good to know. Now the trick, and there's a reason I'm telling you this because we're just about done. The trick in all of this is deciding when do you just directly solve. Okay? Sometimes it's not all the way down to the 1 or 2. Like if I had a loop I was splitting up this way, I might say, I'll direct solve when the loop is down to 100 iterations. So think about closely about how to solve that. Now the reason I'm saying that is because the exercise we're going to do after dinner, for those of you who want, is go back to your Pi program. First, create a recursive Pi program based on this divide and conquer approach. Once you have a recursive Pi program working, parallelize it with tasks. Really cool. That's like a 20 to 30-minute exercise. But if you really want to understand tasks, or really want to see if you understand tasks, this is a good one. And it also gets you into recursive programming. Okay, so I just want to emphasize, I believe we've covered everything on this list. This is the entire OpenMP Common Core. And I cannot stress enough, most of you in a serious OpenMP career will never need to go beyond these 19 constructs. You have learned enough of OpenMP to do serious professional level OpenMP programming. My advice to you is spend time with the Common Core until it's all second nature, until you can do very, very deep, intricate programming with the OpenMP Common Core. Then learn the other stuff. So there's a lot more to the Common Core, but what I want to talk about is there's this book, Using OpenMP, the Next Step. So after you've mastered the Common Core, buy this book, and this is where you go to the next level of expertise in OpenMP. Now, I am serious. Buy this book, but I want you to notice my name is not here. So it is not inappropriate when I tell you to buy that book. But if you see Rude or Eric or Christian, tell them, Tim said to buy your book. And if you do that, they might tell people to buy my book. No, this is a great book. The problem is, it's been phenomenally successful. It's still selling even though it came out in 2004, which is unusual for a specialized computer science book. It's out of date in that it didn't anticipate the GPU emergence. And it downplayed vectorization. So it's a little bit out of date, but I don't know. People are still writing lots of code that aren't on GPUs. This book is around 300 pages. The second edition of it that we're still working on is now over 650 pages. So that tells you when you start going down, oh, we got to handle vectorization. Oh, we have to handle GPUs. Oh, we have to handle the interaction between GPUs and CPUs. And oh my God, does it get complicated. But at any rate, yeah, I'd love it if you bought my book. But seriously, buy this book. It's the book to take you beyond the Common Core.